join button. Well, yes, I hope everyone who has joined, you are all doing well in this difficult time. In fact, our opening remarks is nothing but a series of thank yous from us, the organizers, to all of you. And first of all, the first thank yous goes to the authors, to all of you who submit your paper to our workshop, and to the ones that had their papers accepted. In total, we received 7 papers, among which we accepted 5 papers, which will be presented today during the workshop. Yeah, thank you for keeping up with all the deadlines, with all the changes in the plan, in the program, in even the templates of the LaTeX, everything. Thank you. And the second thank you goes to the program committee, which did a fantastic job. I personally went through all the reviews to select the papers. It was very nice to read the reviews. I would like to thank them, although they are not at the moment here, most of them. But this was a pleasure working with them. So thanks to them. And last but not least, thanks to our speakers, Professor Danica Krajic, which will be the first speaker of today, and Professor Walterio Mael Cuevas, which I assume will be joining us a little later. It's just a little too early for him in USA. And yeah, we will be hearing their speech today. And this will be the program of the workshop that we will be going through. After this short introduction, we will be starting with the talk from Professor Krajic, and then we will be having three papers, one after the other. Each of them are supposed to be taking something about 15 minutes or a little less, with about 5 minutes of question answering. And then we can be having a short coffee break, or yeah, if someone wants to take a rest or something. And then we will be coming back here about 4. And just very few remarks. There is not much to mention, just that, yeah, this situation is a little bit strange, at least for me. It's my first time engaging in a workshop or conference virtually, but let's make it look like real a little more. So do not hesitate to raise hand, engage in the talks, express virtual emotions or something. And yeah, please keep your microphones off. I think I already made your microphone off, but please, if possible, keep your camera on, because we would like to see you. And yeah, this one, please do not hesitate to clap actually if you like a talk. It's completely okay. It's a little weird, but you can do it. We can do it. And the last thing is that the session is being recorded. I know that whoever is joining already has signed a form for this, so they are informed, you are informed. But this is just another reminder that the session is being recorded. And that is it. I think we can go on with introduction of our first speaker. Professor Danica Krajic is a professor at the School of Computer Science and Communication at the at the Royal Institute of Technology, KTH. She received her PhD in computer science from KTH in 2001. Currently, she's the director of Center of Autonomous Systems. Danica received the 2007 IEEE Robotic and Automation Society Early Academic Career. She's a member of Royal Swedish Academy of Engineering Science and Young Academy of Sweden. Her research is in the area of robotics, computer vision, and machine learning. In 2012, she received an ERC starting grant. Her research is supported by the EU Knut and Alice Wallenberg Foundation, Swedish Foundation for Strategic Research, and Swedish Research Council. Her talk today is titled Vision for Action and Interaction, from Grasping to HRI. So please, let's welcome our speaker. The stage is yours, Danica, please.
Thank you so very much. So, I just realized I need to shorten down my kind of like this bio, so not to steal too much of the time. But thank you for inviting me. And I will not be able, I think, maybe to see when I start sharing my screen, the reaction. So if there are questions or anything like that, speak freely, if I can say like that, and I will attend to questions during my talk if any come up. Okay, so I think that you need to stop sharing for me to share, I
I am
suppose.
really trying to find the button to stop sharing. I do not know where is it.
It's on the top. If you
Yeah, found
click on
it.
it now, it works. It's usually on the top, but let me see. It will be this one. So I suppose you can see it now. Yeah, right. So I do see some faces on my left-hand side, but not everybody. So again, if you feel like asking questions, please go ahead and do that. So, this workshop is about applications. So I wanted to kind of like dig back some years and talk a little bit about both the work that we are doing now, but also the work that is a little bit older, because I think that in the age of deep learning and the methods that we are using right now, we also have a tendency to forget lots of the older work. So I wanted to go back a little bit and provide a little bit of motivation for the work that we are doing regarding egocentric vision, but also, let's say, working or dealing with multiple sensory modalities for, as I said, action and interaction. So let me see what inspires us, or what kind of like motivates most of our work. So for the past, I would say 20 years, I've been really, really interested in getting robots to do things that we humans do, as I usually say, without thinking. Of course, it's powered by lots of training since birth. But I think that when we, do our daily tasks in interaction with the physical environment, we do this effortlessly. And I would say that most of these examples that I have on my slide here are still impossible to do by robots. The reasons are many, because we still don't have robots that are embodiment-wise similar to us humans. They don't have the perceptual capabilities, but it's also because it's extremely difficult to integrate lots of research that comes from control, perception, machine learning, and so on, to actually demonstrate or have robots to do this again in unstructured environments. So one can, of course, pose a question: do we want robots to do all these things? Why are these relevant? Of course, there are many applications where robots are still, as I said, much lower than humans, maybe will never be used. But I think that from the perspective of actually understanding also the physical world, and understanding also the human better in interaction with physical systems, I think that it's extremely necessary to build robots, even if at the end it's just a tool for understanding the human better, rather than exchanging human doing all these things in natural environment. So bear with me, that's kind of like, so it's not again a tool to exchange a human, but really to some extent understand the human better. So what are the examples of things that we work with, and how do we study these things? So of course we have let's say regular pick and place kind of tasks that comes from one of the Amazon picking challenge. A robot that is equipped with egocentric vision, of course, several cameras, but also with various types of tactile perception, force torque sensing, laser, and so on. And as we can see here, I think that even if we still consider these tasks to be pretty, let's say, the environments are not completely unconstrained, but still robots exhibit lots of difficulties in doing something that we humans, in terms of pick and place, consider rather simple. Why is it difficult? Well, it's difficult due to, let's say, dexterity of the robot is nowhere similar to humans, and it's extremely difficult also to let's say, use perception properly in terms of also having a flexible body that would allow us whatever type of or whatever field of view or the direction of viewing we need when things get, let's say, deep into the shelf or where the object is dropped and things like that. So I think that what is important to remember is that vision in humans is something that is integrated with also lots of activity or action that the bodies do. And I think that that makes also perception in humans easier, and it's still a big challenge for robots. Other problems that we work with have to do, let's say, with learning of highly dynamical tasks. I think that this one plays. Let's see if it does. It's a robot actually learning how to throw a ball. And from there, I will come back to that video anyway later on. So the idea here is that the robot uses, again, the perception, egocentric vision, to understand how to actually generate the right velocity commands for the arm in order to be able to hit one of the objects in the scene. And of course, we can think of this being a highly high dimensional, let's say, learning problem, because we can think of a scene just being a raw visual data or sequence of images, and then the robot is controlled in a whole trajectory space, might be like 20, 30 time instances of 7 degrees of freedom of a robot arm. So it's, let's say, highly dynamic and difficult to represent. So the machine learning methods come definitely into play here. Other tasks they have to do with more human-robot interaction tasks address two types of problems. One is about skill learning and skill transfer, and of course collaboration without the actual physical interaction. So in this case here, the human is performing, let's say, a household task. It might be like baking, or it might be doing dishes or something like that. And the robot's role here is to help the human to be or act as a third hand, understand the context of the task, the activity that the human is doing, and then being instructed either by the dialogue or by observing the scene and trying to understand what the human needs more of, and then be as a helping hand. And another, of course, task is something similar to that, but more related to the physical interaction, where a human and a robot would carry something together. And I think that, well, here it's an interesting example because it shows lots of difficulties, not only for the robot, but also for the human. It's not clear for the human very much what the next step for the robot to do will be. How does the robot communicate what it will do? Is it, again, language as humans do, or is just the expectation of that the body that we collaborate with, or the human or the robot, actually has some, we use our predictive capabilities to understand what the most likely next movement of the robot will be, and we adapt. Now here, the adaptation needs to be done through, for example, direct contact, forced work feedback, and so on. And the vision here is, of course, used very much to understand what the human is doing, because not everything can be sensed through just forced work feedback in the wrist of the robot. So then there are also tasks that require various type of scene understanding and also mapping that to capabilities of robots. Like in this, for example, in this example here, the robot is not able to pick up a spatula, maybe with a parallel jaw gripper if a spatula in a certain configuration. So we worked a lot of developed methods for pre-manipulation, where then one part of the body is used to prepare or to bring the object in the pose from which it can be safely grasped, and also grasped for the task. So in this case, the spatula is grasped, but the robot can actually not use it for flipping a pancake, for example. So how does the robot purposively move the object so that it's prepared, so that it can be grasped for the task at hand? And then, of course, a little bit more in terms of the collaboration, where we, together with neuroscientists, actually look into the process of entrainment. So how do robots and a robot and a human that have, let's say, a common task of, let's say, balancing a ball, playing a game, and so on, how is that done so that a human does not have some additional, let's say, cognitive requirement on him and her in order to accomplish this task. So the robot should move in a way so that the human can, with the highest possible likelihood, predict what a robot is going to do next. So these are some of the things, again, that require or use egocentric vision, but are also very much exploiting other types of sensing, as I already mentioned, which is force torque in the wrist and tactile sensing in the hand. Now, more recent work, again, very much motivated by also the things that we humans do in hand manipulation. So how does the robot actually use bimanual interaction or two hands to help itself? So if the robot cannot do in-hand manipulation because it has a very simple gripping device, how can the other arm be used to actually reposition the object in the hand? So if you think now of spatula, can a spatula that a robot holds somehow be reoriented or repositioned by another hand, either by, for example, pivoting, so robot using dynamics. I don't show these examples here, but we have work on that too, or actually by a set of pushes while the stable grasp is kept. And then, of course, maybe a little bit more advanced example, holding a firm grasp of an object by actually doing finger gating. So something that we also humans use very much. So if the, for example, glass that you hold on becomes heavier because you filled it with a fluid, or because there are some external forces acting on it. So for example, you try to put the glass in a dishwasher, or you put it in a cupboard, but you don't have a complete let's say exact pose estimation. You don't know where exactly the hand is. There is potentially a contact. So while putting something in the shelf, you may move it. So how does the robot remain a stable grasp? So this is also something that can be done as a combination of using egocentric vision and, of course, tactile sensing. And it's still kind of like, I would say, something that not so many robots can demonstrate as a capability. So how to adapt to external disturbances, how to adapt to change conditions in the object weight. And what is interesting here is that, again, in order to be able to firmly track, for example, the object, or to assess the change in other attributes such as weight, one needs to combine various types of sensing. But as I usually say, show this video, I think that this continues to be my motivation. I mean, when we look humans into doing something very skillful, such as washing dishes and so on, not everything is about only a single object. So, of course, we use the interaction between two hands, but we also can do this in different media. And this is something that is really important to remember, that the physics changes very much when we interact with objects in the air, or when we do this in, let's say, oil or dishwashing powder and so on. So that completely changes the stability of a grasp. Also, there are other attributes that we need to know about, such as, for example, how do we understand that the ball is made out of porcelain or maybe plastic, that also affects how firmly we should or can hold it, and what slippage maybe can occur and things like that. And many of these things, I mean, when the object is covered in a dishwashing powder, or it's, it's heavily occluded, and it's also maybe dirty prior to being cleaned, it also affects very much what techniques we can use in order to have a firm and stable tracking of the object pose and so on. So there's still many problems, I think, even with the pretty advanced techniques that we have today, and that I think we will be hearing about during the whole conference, but also this workshop, need to be tested in environments that actually challenge it from several points of view. So not just kind of like pose being changed, but also occlusions change the reflection or reflectance properties and so on. So let me skip this one, just to wanted to have a couple of examples that grasping is not only about really holding an object, but it's also very much about planning where to grasp purposively for the task we need to execute, or the robot needs to execute. And the example in dishwashing shows you that there are so many different types of grasps that the human has applied on the object while rotating it in the hand and washing it and so on, to the process of actually keeping the firm and adapting the grasping conditions based again on, for example, change friction conditions due to the surface properties being changed because the material interaction really changes when you have object covered with oil or water and so on. Now, why is this interesting to study? For me, it has been interesting to study these tasks or these types of tasks for the past 2 decades, because it is interesting from the control perspective. It is interesting from machine learning point perspective, perception perspective, but also, as I said, HRI and so on. And I think one of the difficulties, if we really want to demonstrate and assess this on robots, also shows that, well, the robot hardware changes. So PR2 that we maybe used 10, 15 years ago has been exchanged with Franca robots that have completely different properties and so on. So I think that it's not only that we learn very much about, let's say, the techniques that come from different areas, research areas, but it's also what kind of embodiments can be used, or how can these embodiments available on the market, how these can be used in a proper way to actually address some of the tasks that we are doing. And that also, of course, gives us an understanding what can be transferred between different types of embodiments and what cannot, what's specific for the specific type of embodiment and so on. And of course, one of the things that I think has been a red thread for our research is that many of these things need to be done in real time. It's highly dynamic, which means that it needs to be done online, and the assumptions that follow with, let's say, both control algorithms, machine learning algorithms, and so on, is that some things can be, of course, learned offline, but whatever we run online needs to be real time and needs to go basically even faster than camera sequences are captured and so on. And the example, of course, are the highly dynamic tasks of, for example, throwing, or when something starts to slip from the hand and so on. It requires, as I said, pretty high frame rate. Now, these problems that we are all addressing, and I think all the attendees of this workshop already know, this is also interesting a lot, very interesting for the neuroscience area too. Why is that? Well, from one point of view, neuroscientists would like to transfer whatever they know about humans to robots, but it's also vice versa, because we also give them an idea what is relevant to be measured in humans in order to understand it better. And it's also then the interaction between the human and the robot. What kinds of algorithms now all of a sudden should we be using for entrainment, for example, and let's say fruitful collaboration between artificial systems and humans in order to be able to also, for the humans to continue to use the same type of processes that they use if they collaborate with a human or with a robot. And that's, of course, relevant if we are to use robots for people with special needs and so on. Again, it shouldn't be an additional cognitive burden for them to collaborate with a robot. So I said a little bit about the vision or egocentric vision being really relevant for the tasks like this, but also what I see too little, I would say, nowadays in the community is the ability also to use more than one camera and use the interaction between, let's say, static and moving cameras. So just to give you an example, so this is from 2015, we already had a system that kind of like used 3 cameras in real time, and these 3 cameras come, so there is a camera in each of the robot's hands. So these are 2, and then the third is the Ego Vision, of course, that the robot has. So the idea here is to actually use cameras in the arms to provide additional feedback when the occlusion happens. So we could demonstrate here that we could do tracking in 3 cameras, that we could calibrate that very well, and that choose which feedback to use to compensate, of course, for occlusions and things like that. And why is this relevant? Well, in the beginning, I said that robots still do not possess the same flexibility in their bodies as we humans do. So we can easily, change the view by moving the neck or moving the trunk. And that's not something that robots can do. So it's extremely important that we then equip those parts that are moving in robots, such as, for example, arms, with this additional sensing. And whether we can call this Ego Vision or something else, that's a different story. But again, it's very little work, I would say, nowadays being done on the aspect of how do we integrate several cameras in order to be able to provide these various views of the objects. And I think it's extremely relevant to do even simple tasks such as this dishwashing. And then, of course, there are things that we are studying now that has to do with adaptation a lot and also with knowledge transfer in interaction with various types of objects. And what we also realized here is that many of these things, such as, for example, cutting, shredding, and so on, yes, we can use information that comes from vision in terms of instance recognition or trying to understand where the object is or how it moves. But it's still extremely difficult, let's say, to understand whether a potato is cooked or raw, what its hardness is, and how to hold it, how much to squeeze, or how to cut. Dependent on whether it's, again, raw or 3 days old or 10 days old banana and so on. So I think that this is really interesting, and we will see more of that, how to again integrate force torque feedback or tactile feedback together with vision in order to have this different sensing being used in the best possible way. Now, I want to also say a couple of things about the work and the methodologies that we use to address some of these tasks. I would say that during the past 3-4 years, we have been concentrating very much on state representation learning, with looking into how we can assess or use this entangled representation in order to provide some of the input to the control algorithms to execute some of the tasks that I have just shown you. And why is it relevant, or what types of problems can be addressed? Well, we want to look into having representation that are relevant for the task. So I want to understand, how should I grasp a spatula in order to be able to flip a pancake with it, for example? How do I represent that? How do I generalize over different spatulas, or how can I understand that a very flat and wide knife can be also used as a spatula in certain cases? So what is that is making a certain object or an instance or a category relevant for the task, and how is that represented? I also want to do this embodiment independent. So I want these representations to be relevant for various types of robots, independent of whether the arms have 6 or 7 degrees of freedom, whether this is relevant, or whether the robot has 2, 3, or 5 fingers, and so on. I would also like my representations to be able to take care of multisensory data. So as I think was also easy to some extent understand from some of the examples, Vision is not enough. Sometimes vision and tactile feedback or force-torque feedback can also be redundant. So we need to either decide which one to use or also how to integrate them in order to be able to execute these tasks. And we need to be able to do this online. We need to also kind of like learn from examples. So sometimes we need to understand that even if there is a single object to be shredded, such as, for example, cucumber, and it may be so that even for that, even if it's a single object, the properties of let's say how hard it is that all parts do not remain, so that changes. So we need to be able to continuously kind of like update the models while doing this physical interaction. And there will be also physical parameters beyond shape. As I said, friction is extremely important. So understanding the properties, whether the objects are rigid or deformable, and then having methods that can properly adapt to that. So we've been looking then, of course, very much into the combination of analytic and data-driven approaches. So something that can be then represented because we just know it, because it's kind of like physically realistic to represent it. We don't need to do everything data-driven. There is no point of doing that if it kind of like makes the problem easier. But also some things cannot be analytically represented, or it's maybe too difficult to actually represent it analytically. So then we can actually set it up as a reinforcement learning problem, for example. That's where data-driven comes into mind. But the bottom line is, if you want to do this on robots, some things can be learned in simulation and transferred. I'm going to say a couple of words about that. But many of the things are very much dependent on the type of the embodiment that we use, plus that the properties of the embodiments can also change. So what kinds of velocity a robot can generate can, due to wear of the robot, change and so on. So the robot will also need to adapt the model. So there is no only a sim to real gap, there is also sometimes real to real gap, just because the properties of the robots change over time. So how do we address that? Now, one of the things we looked into are, of course, various types of representations and what spaces, what mathematical kind of like foundations can be used in order to represent the data. So we can talk about Euclidean spaces, and that's something that is extremely natural when we work with images, when we work with 3D data and so on. But in certain cases, topological kind of like data analysis also makes sense, or topological data representation. So when we look into the tasks of interacting bodies, for example, a robot dragging out a human from the water or helping a human to stand up, we look very much into how various types of linkages interact, and how can we then develop control algorithms based on representations that do not take into account, let's say, regular rigid body representation with a skeleton or anything like that, but look into various types of, as I said, linkages and the interaction between linkages to define the basis for the control. We also worked for quite some time on, let's say, understanding human grasping, understanding human hands, human interaction with the objects in, let's say, various types of contexts. So what are the most common grasps we usually use if we are to, I don't know, pick up a hammer for hammering, or picking up a hammer for putting it in a box and things like that. And this was very relevant work, and some of our early work already almost 10 years ago now looked very much into how probabilistic methods can be used to encode this with Bayesian nets and so on. And that was very early work. It was very much data-driven, again, without deep learning. And now we kind of like started to look during the past couple of years also how the deep learning models can actually be used to address exactly the same things. So I think what is interesting to see is that, well, the problems, I would say, still remained the same, but the methodologies that we use are a little bit different, and also the type of data that we can encode. So what exactly do we look into? So, for example, we look into how one can then, relying on mesh-like data or point clouds, encode various types of object features that are somehow related to the task, but also can be used to define stable grasp. And lots of these things, and I think that both ICPR, CVPR, NeurIPS papers very much are about this. So how can we represent, let's say, objects, 3D point clouds and so on, to generate relevant grasps? But very few of the works that you will see is how can you then use this on a robot and adapt whatever has been generated here to actually execute stable grasps and understand whether the grasp actually is stable, not just because you generated a stable grasp from a, let's say, some deep net or something like that, but it's because a robot can actually use the grasp object in a task. So there are several problems, of course, that can be still addressed. How, in the best possible way, we define various types of instances and categories. What is, let's say, shared between different categories, how these are relevant for the task. But for us, mostly, how can robots learn this grasp from very few trials when something has changed a little bit in the object? And what can be changed, as we said, it might be physical conditions that change. So there is no system in the world right now that will understand that when a certain instance is covered by oil, the grasp that has been generated is not anymore relevant, because that has not, it hasn't been represented in the visual data that the algorithm has been trained on. That's potentially something that can be learned either through the right process, of course, of having that physical model, or by the robot interacting and understanding the contextual knowledge of interacting with the object. And here there are many examples of how this can be done online in a smart way by using different types of Bayesian optimization, as we use it here. So generating kind of like smart, doing smart sampling in a way, and understanding how to do the adaptation after something has been learned offline. We looked also very much into what we can kind of like learn from egocentric sequences of humans interacting with objects, how we can also use that to, let's say, encode the relations between the object and the hand, and understand what the stability from the, let's say, task related grasping actually means. So if the human is to pour wine from a bottle or just move bottle from A to B, how do we encode that so that it makes sense from the, let's say, stability point of view, and how can we also learn to estimate pose and shape of handheld objects from RGB images for the purpose of, let's say, a robot maybe being engaged in a handover task with a human, or just learning what a relevant grasp for the task might be. I'm not going to go into details here, but this is also kind of like a combination again of using the human using perception of human interaction, and then adapting it for the robot to kind of like be able to execute various types of task-oriented grasps that are, again, relevant for tasks such as, for example, screwing or pouring and so on. And then one of the things that we also kind of like recently realized, especially when it comes to robots that need to interact with objects in the real world, is that maybe the shape of the object will not be available from the beginning. I jumped a little bit into this video, but the idea here is that we build, let's say, graphs of the object incrementally, and the graph is built not to just understand the geometry or build a full shape of the object when it's not, for which the shape is not known from the beginning, but really for the purpose of moving the object in the hand in order to be able to do that. So we use what we call dexterous manipulation grasps, so that the robot can, through a set of pushes and through the set of rotations, actually get a better 3D shape of the object, and really through the interaction also understand, for example, is this a real hammer or is this a toy hammer, because the distribution of the weight is what I wouldn't expect. So if you have a plastic knife, or if you have really a wooden knife with an iron head, the force distribution will be very different, and how the interaction in the hand is then done, that also affects then the process of planning of how to do the pushes. So I think that this is really interesting, because it kind of like shows the additional challenges that we need to put to the systems that are currently based solely on vision. So understanding again whether it's a toy or a real object or a real hammer is we are able to do that solely through the actual physical interaction. Now, for the past, I think, or the last 5 minutes, I wanted to kind of like go through the couple of examples of the things that we also did in terms of like reinforcement learning and why reinforcement learning is relevant. I already motivated it in the beginning, one of the tasks such as throwing, so learning the full dynamics of throwing, dependent on where the object on the table is. Analytically is really close to impossible to do, or I would say impossible. So we look into data-driven approaches of how to do that. And we do this by, let's say, using various types of encoder, decoder kind of like structures, where the idea is to address the multidimensionality of this problem by understanding that, well, even if the robot kind of like needs to do a long sequence of motions in 7-dimensional or maybe 14-dimensional space of velocity and accelerations, it actually passes through the same points in the configuration space. So we look into how this latent space of, let's say, low dimensional representation of a scene and a low dimensional representation of the action space can be used in the best possible way, and how the training can be done then in what we call a policy super layer space, because it is a mapping between some low dimensional representation of the image and low dimensional representation of the action space. So we don't need to think of sequences that are, let's say, 20 time frames multiplied by 7 joints, or let's say 14 if you also take velocity into account, but some lower dimensional representation. And this is relevant if we actually want to use or learn things directly on the robot and have very few examples. So we don't want to go from raw image to full 20 by 7 or 20 by 14. We can do this in a lower dimensional space. And what is also interesting, that this makes the whole problem of sim to real transfer also a little bit simpler. So we can generate lots of pickup or throw sequences in simulation. We can do this mapping in that, let's say, low dimensional space in simulation, and then do adaptation online pretty efficiently, just between images or just between actions, which I think it's a very kind of like natural way to think of it. And I think that this is an interesting type of structure, because it can also kind of like address in-hand manipulation and hand motions and things like that. So also when the contact is present, but we need to kind of like then have a better maybe representation for the pose of something in the hand, which then fits back to some of the, let's say, using several cameras for perception and things like that. Now, as the final example, some of the one of the things that I would like to do, and which I think we are also kind of like looking lots of people, seeing lots of people moving into, is interaction with deformable objects, of course. Deformable objects, we can think of clothing items, we can think of anything that kind of like has a soft structure and that somehow does not have a very well defined pose. So what do I mean by that? Well, if you want robots to iron similar to what humans, how humans iron, or if we think about assistive dressing, so robots putting or humans putting clothes on humans, we need to somehow understand where the openings of the shirt are, or how do we grasp a shirt in order to be able to drag a sleeve on somebody's arm and so on. And nothing here is, I would say, easy to do, not from the perception point of view and not from the control point of view either. So what we started to look into is how can we use then data-driven methods to perform what we call visual planning. And this example here is considering the task of folding. So of course that the pose will not be unique from the beginning, because there might be small creases on something that is not completely flat. There might be kind of like various types of shirts and so on. So we are looking into how we can then generate an action plan, which is a sequence of actions to achieve these consecutive transitions of, for example, folding, by have some latent representation of the visual plan. So how the things change. So how do we do that? So again, we study various types of space representations. So we want some form of a low dimensional representation that can be then used for planning, where we say we have a starting state, which is the initial state of a shirt, and then the goal might be the folded shirt or shirt on somebody's body. And then we look into, again, different types of encoder-decoder structures with some latent representation, where we can do or perform this kind of like action planning. So we want to understand of how to go from the start or the current image to some folded state. And as I said, latent variable models, and how do we capture the transitions? How do we say that there are like two visual observations of a shirt that are actually connected by the action? So what does that mean? Well, it means that if we have something in this state, the next state might be, or the action performed might be to grasp the end of one sleeve and put it on the shoulder point. The second might be the second sleeve, put it on this shoulder point, and so on until the folding is performed. So we want to understand that an action of picking up something and putting down is not going to bring this sleeve behind the front part of the shirt, but that it's actually going to be on top of the shirt. And that the connection between the action of where, or the state where let's say that point would be under the shirt, is actually not a valid kind of like action, and should not be the part of the action plan. So there's many interesting problems here. The first one is, of course, how to extract the states from observations, and then how to connect these to relevant actions. So also take the embodiment into account, what can be actually done by the robot, and so on. We use variational autoencoders for the representation. If somebody is interested in details, I do have citations to the paper at the bottom. But what the interesting thing is also the use of contrastive learning. So it's not only what states are close together, but also kind of like those states which are not connected by the action, or there is no action that can bring two states close to each other, one state to the other, so to speak. We put it as a contrastive loss. So not to bother you with everything, we have a data set that is available where we have a number of examples of a robot folding things, and also having the visual perception. Again, egocentric vision here is very relevant. what actually brings a shirt from unfolded to a folded state. So this is just one of the examples to show you a difficulty. So that would be a start image. This is something that we want to end up with, and the system can generate a set of states, so to speak, that instruct the robot of what to pick, where, and where to put it down. And as one can understand, there are many things that can happen here. So for example, that the grasping action is not successful, or that maybe a part of the shirt is dropped while being moved and transferred and so on. So actually we want to have a possibility of also replanning. So we want to kind of like assess after every motion or during the motion where the shirt is, what has potentially happened, gone wrong, and also replan. And this is why it's extremely important to have kind of like a representation of the full action space that is related to then the visual representation that can allow us to do that. So I think that I'm going to stop here now. I will stop sharing my slides and stop with this slide here that I showed in the beginning. And hopefully this gave you a little bit of an idea of the work that we do. Addressing something that, again, we humans do without lots of thinking. And I hope there are a couple of questions out there that I can address. So Maya, back to you. Thank you so much.
Thank you, Danica. I am actually trying to unmute everyone. If I find it where I can do that.
I think under participants, you should be able to do that. Maybe.
I can only mute people.
Okay. And then everybody can unmute themselves. So
yeah, it is mainly to actually clap for you because of your fantastic. I'm not from the robotic field, but I pretty much enjoyed your presentation. I want to ask the audience. Yeah, we are having.
They can also write their questions if there are any in the chat window.
May I do a question?
Yeah.
What's the role of anticipation for performing tasks for robots? Mm-hmm. So, in sense of a cooperation, for instance, with humans,
yeah.
How much will be important, because in this moment we are still struggling on understanding what is going on, but to really help humans in cooperating with humans, probably we need to work also on anticipating what is going to happen in few seconds, in 1 second, in short term. Do you have any guess on this? We are trying to do this from first person perception and help humans with a wearable device, but what about the robotics?
Yes, exactly. So a couple of works that we have on that, also tracking humans and predicting kind of like few seconds in the future, kind of like what's the most likely next motion of the human body and things like that. I haven't talked about that today, but I think it's really important because we, as I said in the beginning, realized when we did various types of human collaboration tasks with humans that are not used to being close to robots, like industrial settings, for example. Yeah. So robots can sometimes be scary for people that are not used. So maybe the role of anticipation is extremely important when this kind of like entrainment is done, when the human is getting used to the robot. So somehow we need to kind of like signal for the human collaborator what the robot is going to do next. To address kind of like the issue of fear or something like that. But for me, it has always been also an extremely good input for the control algorithms for the robot. So in order for the robot to kind of like have a plan of where to move or how to slow down, for example, it needs to kind of like understand what the human is going to do next. And humans think that, you know, that we don't do this kind of like strange motions and things like that, and that we can control our bodies, but that's actually not true. And we know that from lots of neuroscience kind of like experiments. When we are a little bit stressed, we don't have a full control kind of like of this kind of motions and so on. And I think that this is extremely important also when we do compliant tasks. So when there is a direct physical interaction between a human body and a robot body. So I think it's extremely important, but there are a couple of challenges I think that we have. And this is that we need to really understand full pose, I would say, not only of the body, but also of the hands too. I think that that's really important when it comes to kind of like physical interaction with, let's say, tools. This is something that we understood for industrial settings. You know, we talk about the third hand and the robot is going to hand over something to a human. How is the pose right? At what frequency is that interaction happening, and so on. So it's not really only about being able to predict, but to do this kind of like continuously, and also have a good way of showing what the robot or where the robot body is kind of like going to be dependent on where the human body is going. So we can predict. So it's kind of like this interplay between the human and the robot for me, very much. And I think that some of the things that we in robotics think, it's important, but I don't see works on that in computer vision, is when the physical contact is present. So that's
human
something,
and robot, right?
human and the robot, yeah. So that kind of like compliance, I think, is extremely important, because it's there where the dynamics happens. So if a robot and a human carry a table together and it's heavy, this is where kind of like the problems are going to occur. So can the robot signal that, well, please stop moving in that direction because you are bringing me closer to a place from which I cannot move my arm anymore? So that the robot kind of like ends up in a, let's say, part of the configuration space where it's locked or something like that. And that can be pretty, yeah. So singularities, that's what I'm kind of like getting to. So I think it needs to, yeah, sorry, it's a very important problem, but I think that it depends a little bit on the context in which it is used, how we address it.
Well, thank you. I would like to ask the participants if someone has any question, please.
If not, they can email me so that I don't steal any more of the valuable time from the workshop. I think that, yeah, just email me and I can provide kind of like more in-depth explanations or give you feedback if you come up with questions later on.
So we do not have any more questions from the participants?
I have one very quick, maybe Maya.
Yeah, okay, please go ahead.
Thank you very much for the presentation. The task of folding is very complex, and really happy to see it because it's one of the 3D aspects which is difficult to regarding the deformable modeling of the things. Do you think forecasting how the actions will change the shape of the object is important for this task, because you cannot encode all the possible, let's say, deformation, because it's not a static, let's say, as it is named.
So this is why I talked a little bit about this representational learning also in topological space. I think that we kind of like need to extract or represent things that are somehow relevant for the task. So, you know, I think that there are ways of using some form of a structured, let's say, representation. that in this case uses the knowledge of, let's say, different parts of a shirt or something like that, like more functional parts if you want to dress somebody, or something else if you want to fold it, or if you want to iron it, for example. So I do believe that with let's say using some of the knowledge, not do everything, you know, just draw image and then we learn from it, but that we extract, that we have one layer that, dependent on the task, has some form of a more kind of like, let's say, lower dimensional representation that provides input for the kind of like for the action space. So from the shirt folding kind of like task, we learned that there are so many things that can kind of like happen on the way, and that let's say just using raw images, it's not I don't think it's going to kind of like work, especially if we want to transfer it also between the tasks, because I think that ironing will require something else than folding, but it's still the same object. So the question is, what remains? Can we use the same type of representation if we kind of like not use raw images, but have some form of, let's say, topological representation in between or something like that? Hopefully it gives a little bit of kind of like direction where we are going, but this is what we are currently looking into.
I myself have another question. It is a more general question. I was just wondering, from the computer vision perspective, from the people working mostly with robotics, when you're looking for a data set, how do you decide where to look for it? Are you mostly like going towards the computer vision available data set, egocentric vision available data sets, or you prefer to make your own, or there are like available data set mostly for like completely let's say there are data sets available for robotic applications? How do you I would like
it's a kind of like, I would say, a combination, and it depends a little bit on the problem that we address. So when it comes to kind of like understanding human hand, human interaction with objects, there are like lots of data sets that people in computer vision have been developing. So of course we go and use that. But then how you transfer that to 2 or 3 or 4 fingered hand, that's like, you know, then you need to kind of like either generate the data yourself to do the transfer, or use like a simulator for doing that, and so on. So we usually combine. One of the recent, I think, transactions on robotics, or letters, robotics letters, had a full volume that was regarding benchmarking on various types of, let's say, robotics tasks. So for example, we had a benchmark for in-hand manipulation and benchmark for interaction with deformable objects, where we looked and needed to generate really a data set for flattening, for example, or folding, because there is nothing there that would kind of like not only give you kind of like video sequences, but you also need to have robot actions related to it. So it depends a little bit on whether we can, let's say, structure the problem solely as a perception problem, or whether we actually need the action to be an integral part of it, because in most cases you will not have, from computer vision, nothing that kind of like relates to the actual robot embodiment. So so we are not generating just for generating the data, but we generate it when it's necessary. But we always go and look what's available from the machine learning or computer vision community to start with.
Great, thank you.
Okay, then thank you so much once again for inviting me, and good luck with the rest of the day.
Thank you so much.
Yeah, bye-bye. Thank you. Bye.
Bye. Bye. Yeah, we're having some virtual claps. So I think we can proceed to the first paper of the session. camera ego positioning using sensor fusion and complementary method. While the first author, I hope I'm pronouncing the name well, Peng Yuan Kao.
Yes, it's a hello.
Hello.
Oh, yeah, let's run. Yeah, I'm here. I'm the first author. But today, the presentation will be going to the second author. Yeah, the Guang Wei Zheng.
So someone else is presenting the paper?
Yeah.
Okay, is he here?
Yes.
Yeah.
Can you hear me?
Yes.
Okay, perfect.
Okay, I'm Guang Wei Zhen, and I'm the presenter of this paper.
Do you mind please to share your screen?
Okay. So
You will be presenting the paper orally, or how do you prefer to do that?
sorry, I have a little problem on recording my screen, so maybe I must leave the Zoom and come back again. Please wait me for a second.
Sure. But probably meanwhile we can proceed with the. Yeah, he left. So yeah, we can wait a few minutes. If not, we will proceed with the next author. Yeah, next paper.
Okay, hello, I'm back. And now I'm going to show my, my screen. So can you see my screen?
Yes,
Yes.
perfect.
Okay, since I record a video, so I would like just to play the video. So, but if there is any question, I and Peng Yuan Gao, the first author, will be here to answer. Okay.
Hello everyone, my name is Guang Wei.
Sorry. Maybe, okay.
Hello everyone, my name is Guang Wei. It's my great pleasure to present our paper, Camera Ego Positioning using Sensor Fusion and Complementary Method. This is joint work of National Taiwan University, National Chiao Tung University, and National Jinan University. This is the outline of our presentation. First, we provide a brief introduction on camera ego positioning. Second, we elaborate on the proposed complementary ego positioning method with sensor fusion. Next, we report the experimental analysis on the proposed method under different scenarios. Finally, we would like to summarize our contribution and make a conclusion.
Oh, okay, so far, can anyone hear very clearly of this video?
Yes, we do.
Okay. And now continue. Okay.
Ego positioning or pose estimation is an active research topic in robotics. There are various appropriate solutions available for robot localization, including laser scanner approaches, such as LiDAR, motion sensor approaches, such as IMU, radio positioning approaches, such as GPS or Wi-Fi, dynamic vision sensor approaches, such as event camera, and visual approaches, which is referred to as visual odometry or visual SLAM. In addition, robot can localize itself with more than one sensor, which is known as sensor fusion. In this work, we adopt visual inertial framework, which contains a monocular camera and a 6-axis inertial measurement unit. There are many kinds of visual SLAM. According to different front-end processing methods, we can roughly divide visual SLAM into two types, direct and feature-based. Feature-based methods perform fast tracking on sparse features by descriptor matching. Thus, it does poorly in textualist scenario or blurriness caused by fast movements or rotation. ORV SLAM is a representative feature-based SLAM. Its decent bundle adjustment strategy with loop closure, which optimizes camera pose and global map, contributes to its high accuracy. However, since it relies on sparse feature, it is prone to lose tracking during fast movement. Direct methods operate on image intensities for both tracking and mapping. LSD SLAM is a classic direct SLAM method, which employs photometric error and geometric constraint using dense points. Accordingly, it can provide robust estimation with the cost of high CPU demand. In this work, we propose an ego positioning method using complementary fusion. It takes the respective advantage of feature-based and direct visual SLAM. The figure shows the framework of the proposed system. The input is the monocular camera frames and IMU measurements, while the output is 6 degrees of freedom camera pose. Main and complementary module process the input separately to get camera pose. Then, we refine the camera pose and get true scale by using inertial measurements with loosely coupled sensor fusion. In complementary fusion, we formulate a criterion to determine which module, main or complementary, provides more trustworthy pose estimation. There are many frameworks for visual inertial fusion, including filter-based, optimization-based, and neural network-based. In this work, we adopt a filter-based, loosely coupled sensor fusion for visual inertial odometry. The state vector contains 8 components. The first to the third components are the position, velocity, and the rotation in quaternion of the body. The fourth to the fifth component are the IMU bias. Subscript omega is for the gyroscope, and a subscript alpha is for the accelerometer. Bias terms are modeled as random walk, whose derivative are white noise. Lambda is the measurement scale factor, and P and Q are the extrinsic parameters between camera and IMU. Lambda, P, and Q are assumed to be constant over time. The filter consists of a prediction and update step. IMU data are used in prediction step for state propagation as the motion model in a basic Kalman filter. The velocity of the body is the integration of true acceleration in world coordinate over time. And the position is the integration of velocity over time. The positioning result is provided by visual SLAM. It is treated as an update step in a basic Kalman filter, where we incorporate a scale factor lambda for alignment between IMU and visual measurements. We apply underperformance detection algorithm to decide which module provides more reliable result. It detects behaviors such as post-estimation drift or tracking loss, which often result in abnormal camera rotation estimations. In our framework, the camera rotation is estimated by 2 different modules, the visual positioning module and the sensor fusion module. Ideally, the camera rotation estimated by the visual positioning and sensor fusion are the same. However, if the visual positioning method underperforms, a considerable difference should be observed. In our implementation, we maintain a median filter with a fixed window size. If the rotation estimate lies outside 3 times of the standard deviation, we consider it as an underperformance incident. And the localization result will be switched to the complementary module. When there is an underperformance incident, we need to switch the result to the complementary module. However, they are in different coordinate system. To fuse 2 visual inertial odometry, they must be aligned. We can estimate the rigid body transform, consists of rotation and translation to align the main and the complementary results by optimizing the objective function. Note that despite the fact that monocular visual SLAM is unscaled, we can obtain true scale from the sensor fusion module with the help of inertial measurement units. Thus, when the main module underperforms, the complementary module will take over the localization by the estimated transformation. To validate our system, we conduct several experiments. We designed a handheld device made out of GoPro Hero 4 and NG IMU. The camera is rolling shutter and captures image at 30 Hz. And the IMU is industrial level and get motion measurements at 100 Hz. The ground truth trajectory is collected by Vicon. We test our method in 2 scenarios, normal and featureless. All sequences are taken indoor with the total traveling distance ranging from 10 to 50 meters. In normal scenario, the result shows that both ORB SLAM and LSD SLAM have good positioning accuracy. The positioning errors of ORB SLAM and LSD SLAM can be further reduced by fusing with the IMU. Moreover, sensor fusion also recovers the scale of the real world. From the plot of difference in rotation, we can conclude that there is no underperformance incident in this scenario, and thus the result or the output of the complementary fusion is that the ORB SLAM with IMU. In a featureless scenario, there is a textureless white wall which makes ORB SLAM lose tracking. Here is the video shows how ORB SLAM fails. At the beginning, ORB SLAM works normally, but when it travels to the white wall, the number of track features decrease drastically, and finally it loses tracking. When ORB SLAM loses tracking, it will try to relocalize itself with place recognition. In our case, it relocalizes after it returns to the place we start. The figure on the right is the trajectory of the sequence. We align the positioning result to the ground truth. The red line is the positioning result, and the blue line is the ground truth. Since ORB SLAM loses tracking at the white wall, there is a discontinuity in the positioning result. Although the visual measurement fails, the state propagation can continue without measurement update. This shows the benefit of using loosely coupled sensor fusion framework. In contrast, LSD SLAM is robust in the whole trajectory. Hence, the proposed complementary ego positioning system can survive by using the result from LSD SLAM when it travels to the white wall. However, as we can observe from the aligned trajectory, the positioning result is not very accurate. This table and figure shows the root mean square errors and the aligned trajectory under featureless scenario. On one hand, since ORB SLAM loses tracking during the process, its error should not be considered. Despite visual measurement failure, ORB SLAM plus IMU is able to keep localizing itself by IMU state propagation before ORB SLAM relocalize. However, the positioning error and scale errors are too considerable to be overlooked. In our experiment, the IMU we utilized is industrial level. The situation will be even worse if we use consumer level IMU in mobile devices. On the other hand, LSD SLAM is consistently robust, but the accuracy is not very satisfying. The loosely coupled sensor fusion improves the positioning result little, but it provides the system true scale. From the plot of Q, which is the difference in rotation between visual positioning and sensor fusion module, we can determine the timing of underperformance incident. After the Kalman filter converged, if there is a drastic change in Q, it indicates that the system underperforms, and we should switch the localization to the complementary module. That is, in our case, when ORB SLAM loses tracking, LSD SLAM takes over the localization process. The trajectory on the right is the finalized output. By combining the localization results of ORB SLAM and LSD SLAM, we can further reduce the localization error, and the scale error is maintained within 5%. In this paper, we propose a novel camera localization method by using sensor fusion and complementary ego positioning. First, we use the filter-based loosely coupled sensor fusion to fuse the visual positioning result with IMU measurements to yield a refined pose and true scale. Furthermore, we combine the ego positioning result of feature-based SLAM and direct SLAM to achieve better performance in featureless scenario. The experimental result shows that in normal scenario, sensor fusion improves the visual positioning result and estimates the scale of the real world. In featureless scenario, the direct method takes over and maintains a robust result. Thanks for your listening. If you have any questions, please feel free to ask us.
Well,
Okay.
Nice presentation. We are running a little late with the schedule, but probably we can be taking one question if there is any. you can just raise your hand, please.
I have one question, if there is no other.
Yes,
Okay.
Okay, so basically I wonder, obviously there can be lots of situations where the tracking quality can be affected. I wonder if you ever observe in these conditions, I don't know, let's say there's a fast movement, for instance, how your model is behaving. Can you comment on this a little bit?
I'm sorry, but I'm not quite understand what model is in your question.
Your method, I mean.
Oh, my method. Okay. So basically, ORB SLAM lose track easily in featureless scenario when like travels to the white wall, or if the movement is a little bit faster than standard walking, like running or quick rotation. Especially for rotation, we found that it is quite easy to make ORB SLAM fails because it requires a lot amount of feature to maintain robust tracking results.
Yeah, okay. Yes, this was my assumption as well. Thank you.
Okay.
Thank you for the presentation. I would like to ask you please to stop sharing your screen so the next the author of the next paper can start sharing his screen.
Right.
Yeah, the next paper is at SAL, an attention-based architecture for saliency prediction in 360-degree videos. Yasser Dahu, the first author, will be presenting it. I understood that, Yasser, you also want to play the pre-recorded video.
Yeah. So hi, everyone. Can everybody see my screen?
I think we do see your screen yet.
Okay, cool. So I'm playing the video, yeah?
We are not hearing anything.
You are not hearing anything. Okay. So I don't know, maybe like the sound is not shared. Okay, I'll play the video. I'll do it now anyway, okay? Okay, just give me a second. So hi everyone. So this is Yasser from Dublin City University. I'll be presenting our paper on visual attention modeling for 360 videos. As a brief outline of the presentation, I'm first gonna define the task at hand, which is saliency prediction. Then I'll show the most common data sets used by the community. Next, I'll describe the framework unifying previous works. Then I'll move on to explain our approach, and I'll conclude by the results. So saliency prediction in general is the task of modeling human attention computationally. So the goal is to build a function f with some parameters theta that produces a saliency map from an input image. So a saliency map, you can see it as a multimodal Gaussian where each pixel has got a probability, whether it is highly likely to be attended by a human when seeing the input image. That's saliency in general. In the context of 360 data, that is usually represented in a 3D domain. So we aim to model saliency on a sphere rather than a 2D grid as images or videos. So this give us like two types of saliency for omnidirectional videos. First, we have what we call the head motion-based saliency models. So these models, they are expected to predict the ground truth heat map derived from the movements of the head only, which is simply the center of the viewport. But we have also head plus eye motion-based saliency models. So these models are supposed to predict the viewport at hand, as well as the movement of the eye within this given viewport. And in this work, we are interested in the later task. We're interested in head plus eye saliency estimation. There is a couple applications of this. So if you are streaming a 4K 360 video over a network, some bandwidth issue will arise due to the high resolution and high quality data. One approach would be to use like a saliency-based viewport adaptive streaming scheme, encoding the salient regions in a high resolution to increase the quality of perception, while smoothing out the rest of the scene in a lower resolution, since we know a priori that the user won't pay attention to those parts in here, those regions in here. Okay. Okay, so the first, you are doing the deep learning, so we need some data sets to train the models on. The first data set has been proposed as part of this Salient 360 challenge that contains about like 25 videos, each labeled both head movements and head plus eye saliency. So this plot in here represents the correlation between the head only maps and the head plus eye maps. And as you can see, like they're not like much correlated, yeah, with a Pearson coefficient less than 0.5. Another large-scale dataset has been proposed in CVPR 2018 with more than 2,000 videos. It is like a large-scale dataset, but this dataset provides only what we call the scan paths. It's not like a saliency dataset. So what we did in the for this paper is we pre-processed this dataset and made it available as a saliency dataset with the heat maps for head plus eye saliency. All right. So now I'm gonna show a general framework for saliency approaches on 360 videos and images. That summarizes like most of the previous works. So this framework has like 3 main stages. So the first stage is sphere pre-processing. Then we have feature extraction, and then we have like saliency map generation. These pre-processing methods are the foundations of the spherical visual attention models. The idea is to project the sphere into a 2D plane to be able to work on it. The main used projection methods are the equirectangular projection method and the cube map projection method. And second, we have like the feature extraction stage. So some people use handcrafted methods, which are like some heuristics, but like most of the people, what they do is they adapt 2D deep learning based saliency models, like for example, Salgan or Salicon, to get like saliency maps on a 2D plane. And then they use like a prior as a like center prior or an equator prior to generate the saliency for 360 videos. Okay, now we're gonna talk about our approach. So the model we propose in the scope of this paper. So the basic motivation of this framework is to show the importance of global visual attention in achieving like better saliency prediction. The design consists of an attention model, expert models, and a fusion method. The approach operates in 2 parallel streams. One stream is for extracting global attention statistics via the attention mechanism applied on the ERP frame. This explicitly captures the static saliency information. The bottom stream is to learn more effective temporal features. So the experts models embed like 2 instances of a 2D video saliency state-of-the-art model called SAL-EMA that is working on the cube faces. So we have like 2 versions of it. Yeah, we have SAL-EMA poles that is acting on the zenith and nadir, and we have like SAL-EMA equator specialized for the equator viewports, sort of an equator prior. So the 6 patches are inversely projected into the ERP format, followed by a Hadamard product with the attention map acting as a feature-wise selection mechanism. So this fusion method will reduce the amount of distortions accounted in here by the inverse cube map projection. So let's see like each component of the model in detail. So the global, like the first one is the attention stream. Yeah. The global attention effect related to omnidirectional scenes, like in general, and for head plus eye saliency prediction, has not been studied well in the literature. Yeah. We address this by implementing an attention mechanism that is able to encode the global statistics of the 360 image or video. So a dense mask is learned at the middle of the bottleneck in here with an enlarged receptive field. And this attention mask is combined by performing pixel-wise multiplication with a latent representation, followed by a pixel-wise summation like among the channels to obtain the final representation that embeds like a global information about the input frame. So the intuition is that like the receptive field of an encoder needs to cover like the entire input space. What this attention mechanism does is it like enlarges the receptive field of our like VGG based encoder from 212 by 212 to 676 by 676, meaning now we can propagate like each pixel-wise response to a field of the whole input image. And actually this is like motivated by the fact that human attention is driven like by both global versus like local features. So global features are like features such as semantics and like the spatial configuration. Called in the literature, they call the scene layout or gist, which guides like basically the early visual search of a human when watching a video. Because like I mean, in omnidirectional videos, the people use this cube map projection. This CMP like projection like forces the model to lose the global contextual information by considering like each patch separately. Okay, so this is the motivation of the first part. The second part is the expert models. So then we have like mainly like the previous works who use like the cube map projection. They learn the same network parameters for the 6 like faces of the cube. However, we have noticed that in the context of 360 videos, the saliency is mostly represented in the equator, forcing like when doing so, forcing the network to overestimate fixations near the poles, which is like one of the main reasons the prediction performance drops. For our setting, the expert stream, like we have like 2 versions of like the 2D video model SAL-EMA, and combine the results through this through the inverse projection. So first, first the input frame is projected into the cube map format, like resulting in 6 faces. Then SAL-EMA poles is fine-tuned on the zenith and nadir, while SAL-EMA equator is fine-tuned on the equator patches. And it is worth mentioning also that SAL-EMA models the temporal domain using an exponential moving average that shows to be better in this case than an LSTM. Okay, our training procedure. So the attention module was trained in 2 stages. So first, like to encode static saliency, we train the model on 360 images only, because static images like they gather like high average of fixation points compared to videos, thus like allowing the model to learn like dense attention maps. The loss function we used is a combination of the Kuhlbach-Leibler divergence and the normalized scan path saliency. It means like we optimize the saliency metrics during the training phase. We also make the attention mechanism as a latent attention mechanism by including the dense mask like in the loss function, as you can see in here, by using KLD. And then we retrain the model in the second stage on videos because like our target is like prediction on videos. The expert stream was trained also on videos like Salience 360 and VR eye tracking dataset. It's like 250 videos, and we use like the binary cross entropy loss for this stream, and then we combine the result at the end. Okay, so before we see the results, we also compare the runtime of different SOTA models on 360 dataset. So as you can see in here, ATSAL is like much faster than 360 specialized models, while like staying within a reasonable, like I would say, range compared to 2D models. On the right in here is the results of only the attention stream, like the first part, on images only, because like the attention stream was trained mainly on images. And as you can see, in those like compared on this Silent 360 images dataset. And as you can see in here, like it is outperforming the models published on the Silent 360 lead board by like some margin. Then we have conducted an extensive comparison of mostly all the published works on, like for 360 works on two main datasets, Silent 360 and VR eye tracking dataset, using the 5 like common saliency metrics like the KLD, the area under curve dot, and similarity metric, and so on. And basically we have two settings. So the first setting was only trained on Silent 360 dataset, and the second setting was trained on the combination of both datasets in the same time. And you can see like also that the best score is marked in bold. And it can be seen that first the attention model and the expert model, they are like separately, they got like good results. And then fusing them both, which is like our model ATSAL, like it is shown that it improves the results, and it is like outperforming like most of the models by a good margin. Okay. Also, we can visualize the results of different models. So we can see that like ATSAL in here produces more, I would say, compact and smooth saliency estimation. Like this is like the ground truth, or the human like generated maps. And here like other models, you can see like most of the models, they what they do is they overestimate saliency because they don't have these global features. They only work on local patches, which means like they overestimate like saliency on each patch, and then when do the inverse projection, you end up with an overestimated saliency, while our model is smooth saliency like compared to others. Okay. I'll conclude this talk by a video that shows the different components of the model. So here we have the ground truth. It can be seen that the attention map in here produces, I would say, global saliency. It's overestimated saliency a bit. The expert models, they are much into the details because they work on patch-based or cube face-based. And then we have ATSAL, which is the combination of both of them using this Hadamard product. It can be seen that it's improved the results. As you can see in here, it's closer to the state of the art. And this is like reasonable and understandable because this Hadamard product, what this Hadamard product is doing is forcing all the non-saliency regions not to be like, not to be shown in the final prediction in here. Okay. Okay, thanks for your attention. And we go to some questions.
Thank you, Yasser, for the presentation. Are there any questions? If there is not any question, we can be moving to the next paper. Well, let's thank Yasser again. Thank you. And yeah, you can stop sharing your screen. So the next.
Okay.
Yeah. Sorry.
Hello.
Hello. Screen is okay?
Your screen is okay.
Oh, thank you.
I hope we can hear the video, the sound.
Yeah. First of all, I play the video of the presentation. After that, I start the question and answer session. My name is Yuta Ide. I'm going to talk about our research, Rescue Dog Action Recognition by Integration Egocentric Video, Sound and Sensor Information. A rescue dog is a dog that searches for survivors in disaster areas. They do not actually perform rescue work. Their main role is to search for people in need of rescue. They paired with humans and searched in pairs. The paired human is called the handler. who manually record actions and verbs explain them to commander. The commander of the fire department makes a disaster rescue plan based on the information provided by the rescue dogs and others. One of the problems with the use of rescue dogs is that the quality of information is questionable, as manual records does not ensure objectivity and verbs explains lack of accuracy. It can be said that more and more accurate information on the rescue dog is required. The Government Council for Science, Technology and Innovation has a program called IMPACT that promotes research and development. As a part of IMPACT, there is a research project called Tough Robotics Challenge, which aims to develop robots for disaster relief. Cyber rescue dogs are being searched as a stepping stone to the development of cyborg dogs for disaster rescue. In order to rescue behavior, Konori Ono have developed a wearable measurement and recording devices. Tohoku University, where Ono belongs, is located the disaster area of the 2011 East Japan big earthquake. Therefore, they are conducting a rescue project. This is a lightweight recording suit for dogs, equipped with camera, GPS, and internal sensors. A rescue dog wearing the suit is called a cyber rescue dog. In this research, we deal with the data collected in this way. The purpose of this research is to estimate the behavior of the rescue dogs from audio, video, and sensor information. We use multimodal rescue dog data, video, audio, and sensor information collected and provided by Professor Ono of Tohoku University. There is a research on two-stream CNN for motion recognition video. By dividing a single video into RGB and optical images and inserting them into the network, action recognition with action feature can be achieved. SoundNet is a research project for speech-based action recognition. A network for audio is trained using video as supervisory data and audio waveforms as input. The temporal binding network is a method for recognition first-person video of cooking. By incorporating audio into the first-person video recognition, it is possible to distinguish between actions that are difficult to distinguish with only video information. In our research, we use the method of audio extraction used in the paper. As a previous study, Araki recognized a rescue dog's first-person viewpoint video using data provided by Professor Ono of Tohoku University. It estimates multiple class levels by passing the RGB image, optical image, and sound from the videos through a network and combining the results. This is proposed as a sound image-based three-stream CNN. In our work, we propose a network model that adds information obtained from internal sensor to this network model. The data used is a set of data collected by a rescue dog wearing a measurement suit while it is being trained. The data is still under preparation by Ono of Tohoku University, and a part of it was provided to us in our work. The provided data is a movie that combines the rescue dog point of view, the handler's point of view, and a third-party point of view that shows the rescue dog and the handler in the upper row. The behavior of rescue dog are labeled by time, and the behaviors are multi-labeled because multiple behavior occurs simultaneously. In our work, we formatted the provided data for learning. In our work, only the first-person perspective of the dog is used to estimate the dog behavior. Since the handler and third-person viewpoint does not necessarily show the rescue dog, only the rescue dog viewpoint was cut out. From each frame of the video, we extracted RGB image and calculate the optical flow between the frames. From the RGB image, the until audio data is about 1.6 seconds over 24 frames before and after the RGB image. The extracted data is shown in the bottom row. From left to right, RGB image, optical flow image, and audio visualized by STFT. The information that can be obtained from internal sensor is time, angular vector, acceleration, geomagnetism, altitude, atmosphere pressure, and temperature. In this research, we use time, angular vector, acceleration, and posure. However, not all of the provided dataset come with sensor information. We will treat the part with sensor information as a mini dataset, and use the one including part without sensor information as full dataset. The number of frames appearing in each frame for each dataset is shown in this table. It can be seen that there is considerable bias the number of frames that appeared among the dataset. We did not evaluate in LAN in our work because there is no sensor information about it. We add the sensor stream, which is the part surrounded by the red frame in the figure, to the previous work by Araki. RGB image from video, optical flow images, audio, and sensor information are each passed through the network, and the results are combined estimate multiclass levels. The part that differs from the method of Araki is the part surrounded by the red frame. After a short period of Fortinet transfer, ResNet 101, which is pre-trained in ImageNet, handles audio feature, and VGG15, which is pre-trained in ImageNet, handles RGB image and optical flow image features. The sensor feature extracted by bidirectional LSTM are used as input to each network. After input to each network, the final output is 11 classes in the fully connected layer. For the sensor information, the maximum is 1 and the minimum is -1. The sensor acquires information approximately every 0.005 seconds. In our work, we used 1.6 seconds of sensor information, so a total of 320 pieces of sensor information correspond to one frame of the image. After that, the final input will be 310 pieces of data smoothed by 10 pieces of data. The dataset we used is a mini dataset with sensor information. We used 80% of the first half of the dataset for training and 20% of the second half for evaluation. Therefore, when compared, we also compared the previous studies with the model trained on the above training dataset and the proposed methods. Jagged confidence was used as the criterion for evaluation. This section describes the differences in the network for each method. The proposed method by Araki, the image feature extraction network, are kept as they are, and the one in which the audio process by STFT is changed to ImageNet pre-trained ResNet 101 is VGG ResNet. A VGG ResNet with bidirectional GRU as a sensor network is proposed method 2. The one that adds bidirectional LSTM as a sensor network to VGG ResNet is proposed method 2. The accuracy of the proposed method 1 and 2 are better than that of the method with a sensor. The proposed method 2 the highest accuracy. Compared to Araki's methods, the proposed method 2 improves accuracy by about 7 in total. Compared to VGG ResNet method, the proposed method, the accuracy is improved by 2.04%. Therefore, it can be said the use of sensor information is essential. The figure shows the accuracy of each method. We can see that the accuracy of the proposed method is improved compared to Araki's method. In particular, compared to VGG ResNet, the accuracy of sniff and stop improved 8% and 6%, respectively, before and after the sensor information was added. The accuracy, bark, and shake has improved by changing the audio feature extraction. The accuracy of sniff stop are improved by adding sensor information. The accuracy of proposed method 2 before and after adding sensor information was higher. Therefore, it can be said that the use of sensor information is essential. We propose an image sound sensor base for stream CNN and estimate the rescue dog's behavior using the proposed network. Recognition of rescue dog first-person point of view video using information obtained from internal sensors. By adding the feature extraction network of sensor information, the accuracy was improved compared to the case of only video and audio. The accuracy of recognition was improved by adding the feature extraction network of sensor information, and the results show the use of sensor information is effective. As a future challenge, the use of time series information can be mentioned. It is necessary to incorporate this information into the system while referring to the network. The verification of sensor information was done on the mini dataset, but since the mini dataset does not have the learn action category, we need a dataset that includes sensor information for the learn action category. That's all. Thank you for listening.
Well, thank you for your presentation. I think we can be taking one question. If there is any question, please raise your hand. Well, if not, I have one question. So I understand that the use of the signals is helping considerably in improving the results. But among the signals, you mentioned quite a few of them. So it is like position, it's the speed, it's the angle. Have you done any further analysis on which one of these signals among all of them are being the most helpful?
Let's see. So let's see. Yeah. This slide?
Yes.
Okay. Oh, yeah. I think Poja is the best. Poja is the best. Best sensor information. Yeah.
Yeah. And were there any analysis on that, or it's just mainly your intuition?
Sorry. In this in this presentation, no information, but background I research only angular vector, only acceleration vector, only posure vector. In this research, posure vector is high performance in this way.
Right. Thank you.
Thank you.
I understand there are not other questions, and we are being quite on time. And I already saw that Valteria is already here too. So hello. I think we can, if somebody wants to take a coffee, take like 5 minutes break, you can be doing it, but we are starting sharp at 4, like in 5 minutes from now, we will be starting. So yeah, we are closing now until 5 minutes. If someone wants to get a coffee, now is the time. Hello, Walterio.
Hello. Can you hear me well?
Yes. Very
Ciao,
good morning.
Good morning. Hello. Hey, Alessia.
Ciao.
Hey, Maya and Sigdem. Thank you. Yes, fine. Just early morning. Sorry that I haven't been able to be in the workshop earlier.
No worries. Thank you for being here, even.
My pleasure.
Even the time difference.
Let's see.
I just tested my slides. Hopefully they're coming.
Yeah, we are having it.
Okay, excellent.
I have to confess that I was not expecting this large number of participants.
It's very good. It's thanks to COVID, maybe.
Yeah, probably, or online conferences.
For one thing, it might help something.
Yeah. Yeah, I think it would be a good idea that even after COVID, they provide this possibility to have the online access.
Now we're ready.
Yeah, at least we passed a few conferences with them.
So, as Valterio, you're commuting a lot, I guess.
Sorry, Alessio, I didn't catch.
You're commuting a lot, I guess.
Well, virtually, yes.
Virtually.
So hopefully you're doing well over there.
Yeah, it's pretty okay. I mean, some restriction, of course. But I mean, we had always the freedom to go to more or less always to office.
Okay.
But the weekends, I mean, it seems we are important resource, so we didn't pass to go to work.
Okay, that sounds good. In my cities in the UK, they are currently not able, well, not encouraged to go to the office.
Yeah, I know the situation is really bad. Well, let's hope we recover soon, so I can come to visit you.
Yeah, I know it's tricky, but yes, indeed, Maya, it's a benefit of the virtual meetings. But you also have a strong program, and I'm sorry I missed that. Hopefully, the talks are going to be online later.
Yeah, this is all thanks to Maya and Chida that organize most of the things. So.
Well, thanks to everyone. Thanks to you, to the speaker especially. Well, everything gonna be online later. We still do not know because we are actually at the moment recording.
You are recording.
Yeah. It's being recorded.
Excellent.
Excellent. Yeah. It
yeah,
will be online. We still do not know when and where exactly, but it will be online. Yeah.
Yeah. Hopefully they can be put on somewhere free, not behind a paywall.
Yeah.
We hope so. This is the idea. But they were actually encouraging also, they were encouraging us to like ask for the presentations, for the videos. So we are having all of those too. So the idea is that we later make it available, at least in our webpage of the workshop.
Excellent.
So I think, yes, the organization is pro it.
Maya, I'm just doing a time check. It looks like we are on time now.
Yeah, now is the time exactly. Yes. So welcome back again, everyone. If you've been here listening to the conversation, well, it's my pleasure to introduce our second speaker, Professor Mayo Cuevas. Is a member of the Computer Science Department of the University of Bristol and Principal Research Scientist at Amazon, Seattle, USA. His PhD is from the University of Oxford. During his PhD, he developed some of the earliest wearable computing systems with cameras and jointly with collaborators at Oxford and Bristol. Some of the earliest examples of 60 visual SLAM in real time and its application to robotics and augmented reality. Most recent work includes novel concepts of human-robot interaction, computer vision methods for scene understanding, algorithms for novel visual sensors, and machine learning to assess a skill visually. So welcome. Thank you for being here, and we are all ears. The stage is yours.
Thank you, Maya, and thank you to all the organizers for this. And I hope everyone is safe in these complex times. So yes, indeed, it's my pleasure to be here because egocentric vision has been a passion for me for many years in terms of research and potential. And today, everything I'm talking about is with my university hat. And the thing I want to start with, because I always think it's good to step back and see how things were before, is to talk about something that I did with a colleague, one of my colleagues, Takeshi Kuraja from AIST in Japan. 15 years ago, in 2005, we gave a tutorial about computer vision for wearable visual interfacing. So before this community of research was called egocentric vision, it was called wearable vision. So this already gives you an idea of the type of waves in which this line of work has gone through. And back in 2005, we presented to the community a kind of a collection of the state of the art of how things were at the time. And this is what I thought it would be interesting for us to start with. So essentially, back then, there were motivations and also interests in a number of people. It was a much smaller community, of course, but still there were several people trying to develop these wearable or egocentric visual computing methods and applications. This is an example. This is called stochastics, and essentially this is a work by MIT researchers that put together a head-mounted display. Back then, there were head-mounted displays, maybe not as good as those that are today, but not that far away, to be honest. So a head-mounted display, a camera, and in this case, they develop a method by which you can have some game assistant in pool or billiard, and you are able to detect the table the balls for the game, and actually the system overlaid in 3D information about what the prediction of the trajectories of these balls were. So all in real time. So this is before 15 years ago, because in that workshop we obviously cover some stuff that happened before. So this is 1997, and the system was working back then. Another example that I often find very interesting is this work by Aoki, Schill, and Pentland from 1999. So the topic of personal localization, where are you? Because the assumption is that if you know where you are, then other things can happen. I am in the kitchen, and therefore some of the things that might happen in the kitchen are more likely. And if I am in the living room, other things might be more likely if I am in public transport, and so on. So knowing where you are has been a topic since the outset of egocentric vision. And in this work, Aoki and his colleagues, essentially what they did was show a very robust method that actually works. If you are interested in this space of personal localization, you might want to start trying this method, which essentially is with a camera. The idea is to collect small sequences of frames as you enter an office or you exit a room. So small sequences, small trajectories of video that you put together in a dictionary. And when you want to know where you are after you do this basic mapping or capturing some basic trajectories, you can match them with dynamic time warping. So you put one sequence here, another sequence here, and you try to compute what the distance between each one of the frames is. And with dynamic time warping, you find the cost of aligning these two sequences, because the two sequences may be happening at different velocities. And the method works very well. I mean, honestly, if you're in this space, before you try deep learning or other stuff, you might just want to try this very basic approach. And this has been complemented at the time. This is by 2001 by Clarkson and Pentland with fisheye views. So in this case, they actually put one of those viewers that are using doors, those lenses that are like fisheye. And at the time, there were no GoPro cameras and stuff like that, but one camera at the front, one camera at the back. You capture images. You do something similar to what I just described in the Aoki approach, and you essentially have a very good idea of where you are, even across different times of the day and seasons and so on. So remember, this is a flashback from 15 to 20 years ago. Another piece of work that at the time I found interesting, and again is something that I have seen recently, people attempting with more complex systems with deep learning and so on, is how can you create summaries of your daily life. And actually, this is a work presented by Phil Cheadle from HP Labs in Bristol, and he presented at ICPR back in 2004. And essentially what this did at the time was, there is a camera here on the head, and using vision and inertial information, the system decided, as it was continually recording video, it decided, is this good for a picture, or is this good for a panorama? So if the motion of the head kind of called for a panorama, it detected that you were doing this panning motion with your head and therefore produce a panorama. Or if it saw specific action happening in the scene, it triggered a video. So it decided automatically, is this a picture, is this a panorama, is this a video? And it actually produced these summaries with very basic computer vision methods. Back then, here is my colleague Takeshi and myself. Back then, there were also quite a lot of interest on where are you going to put these extra cameras. So is it going to be in the head? Is it going to be in the chest? Is it going to be in the shoulders? I have recently also seen some works of people revisiting ideas like this, that putting a camera next to your hand so that you actually can observe what the hand is doing, or are you going to put cameras on your feet so that you can capture some of the motion that is happening? So maybe to some degree, some of these things have been resolved, not necessarily in an overly satisfactory way, because I think there's still a need to consider where you are going to capture your images from in egocentric video. But maybe when I said it has somehow been resolved, is forcefully resolved by adding by saying that, well, the available cameras are either big or small, and they're either on your glasses, or you are going to put them on your chest or your bicycle or something like that. But I think there's still quite a lot of thinking that needs to go into from where you're going to capture the world, and therefore some problem like this still exists. Back in the day, like more than 20 years ago, there were also some interesting thoughts about how can you combine cameras with other sensors. In this case, this is the work by Haley and Picard, and they developed what they call the startle cam. So the idea is that the person was wearing a computer. So there's a laptop that is being worn here. There is a camera in the chest, and there is a galvanic skin response sensor that is worn on the fingers. And the idea of this was that depending on both conscious trigger of the camera or less conscious triggering of the camera, like if the person gets startled or they get excited about something, the camera starts recording. Unfortunately, these sensors, this type of galvanic skin response sensors and other sensors that are meant to measure this type of changes from basic inputs like the change of resistance in the skin are not very good. And so this is still like an open question. How can you get better triggers in order to decide when you want to capture things? But I'm just putting this as an example of some previous thinking that has gone into how can you combine the capturing of cameras with more than just the visual images that are in the world. People were also interested since the outset on how to provide things like guidance. So in this case, this is an example, again, 15 plus years ago, where a very small computer, a very basic processor and so on, was taking as input some video that was transmitted to a remote person, together with audio and some other signals for trying to help technicians. So this really hasn't properly worked. In my view, there's still some work in terms of remote guidance that I see enormous potential for developing. But even back in the day, people were researching and putting together these type of systems that just with very basic inputs, and in this case there was no visual audio, because sending two-way video is still a challenge. I mean, luckily my talk is coming through well, but I'm sure you have experienced the complexities of sending two-way video across the world. And so audio and maybe other ways in which you can communicate visual information are still kind of out there in terms of research. Okay, and so this is actually the work of my colleague Takeshi Kuraja, who developed this hand gesturing system also in real time. What you see here is he's clicking his password. And what I find quite interesting is that people, even back then, were thinking already in terms of privacy. So as you can see, the keyboard reconfigures as he's clicking so that the numbers are never repeated in the same place, so that if someone is observing you entering your password, they will have a harder time in terms of figuring out what it is. And combining this type of gesturing interfaces with other things, you can do things like activating translation, for example. like in this case. And this is back in 2001. Some of my own work that has to do with visual SLAM and wearables. So this is oh, actually let me optimize for video. Let me start. So this is back then. This is 2003. A work that I did jointly with Andrew Davison in Oxford, where we had this wearable active camera, and together with his monoslam system, we were able to put together for apparently the first time a 6D visual SLAM system that was also able to show augmented reality. The system was actually developed again along the lines of this remote collaboration scenario, where the camera is moving and the remote operator is able to see through that camera, but that remote operator is also able to control the camera because the camera is active. You can actually move this camera. And then eventually you can also put some AR annotations, like here is a telephone, here is a mug, here is a monitor, and the operator could go back and forth on these annotated places in the world without having to ask the person wearing the camera to move in order to allow observation. So back then, where to know where the camera was also quite important to develop. Nowadays, you can have many systems that are capable of doing such a thing. And then this is also part of my work back from 2004, 2005. And these are how to now link some of this hand gesturing in order for either on purpose interact with the world, or automatically the computer deciding what the person is doing, which is this work over here that summarizes what is the person doing by observing their hands. But yeah, let me just play this other video. So this is a system where hand gesturings in real time is connected with the SLAM, and you're selecting features in the environment that you say, I want to add an annotation here. So again, this is 2004 to 2003, and you can do these very basic annotations. Curiously, if you actually have a look at what current systems do, like HoloLens, even the newest version, still they have these hand gestures, which are not different from the type of gestures that people were trying back then. So this is, of course, a natural expectation that things that were developed 20 or 15 years ago are the things that we start seeing in applications nowadays. But what I find quite interesting to highlight is that many of the concerns that are out there, how do I interpret the world? What type of measurements do I take? How can I combine visual information with other sensors? All those things from 20 plus years ago are still with us today. And that's kind of surprising if you think about that, because it just says, it just tells how complex the problem still is. It's not just the egocentric vision problem, it's the computer vision in general as a problem that is still kind of unresolved. But hopefully some of these early works are giving you some ideas in terms of what has been tried before, what may not need to be tried again, and what things you might want to concentrate on. Of course, nowadays we have new methods, but I don't think that's a justification to necessarily go and redo some of the stuff that has been tried with other methods. Or if a new method comes along, like deep learning methods, if we want to do good research, we should try to compare with some of the earlier, much more basic methods that were developed before. And of course, we now have the benefit of hardware like mobile phones. Back then, 15, 20 years ago, mobile phones essentially were not in the picture as powerful computing devices. Now, mobile phones do have more computing device and some other bigger hardware even. And we also have much better and fancier head-mounted displays and things like that, which, by the way, a lot of people are starting to realize that they still lack or are not actually the bottleneck in terms of making the next step for providing, let's say, assistance. So overall, I do believe there are still several things that are still open as a research problem, and new problems that need to be researched in egocentric vision. And so what I want to talk about next is what exactly I think are a few of those things that are still to be done. This is not necessarily a comprehensive thing, a comprehensive list of everything that needs to be done, but please indulge me of discussing at least a few of them. So in my opinion, dealing with scale and dealing with achieving complexity and scalability are two of the main things that need to be done. How are you going to process these thousands of or potentially millions of frames or seconds or hours of video that that you can potentially capture, not just from one person, but maybe from millions of people? And how are you going to actually scale that capturing and processing and meaningful extraction of information from this mass of data? I think that's still a big problem here. Understanding the context, understanding what's happening, and maybe not just about the location. What is the context? Yes, I am in the kitchen, but I don't need to cook. That would be a very simplistic assumption we can make. How can I really understand what this person needs beyond just where they are? And then understanding the user more in more general terms. So it's not just the context, but also understanding this person, this specific person. How can I realize that this person actually needs help now without the person actually asking for help? So these are three problems, and in my group in Bristol, we have worked towards some of these. So one of the first works I want to talk about is about this: how do you scale the creation of content for assistive XR, and that means mediated reality, augmented reality, virtual reality. How can you scale the creation of content? A lot of people have worked on trying to develop systems that try to guide you on how to do things. But many of them assume that you need these complex displays and maybe very complex setups in terms of I need visual slam in 6D in order to really guide a person. Some of these assumptions I do believe we need to revisit. Even that some of my own work, as we started talking about, has dealt with how to position cameras in the world. Perhaps not always we need to do that. And this work that I'm describing here, which is part of the GLANCE project and funded by EPSRC, is how can we help people when they're facing a problem like operating a machine or repairing a machine. I recently faced this situation myself, where trying to assemble my son's bike, I just spent 5 hours trying to fit one of the wheels, and it turns out that I just needed to find the right piece that is always placed by the factory in a specific location. They never tell you that in the manual, so you spend and waste a lot of time thinking that this thing is never going to properly work, and you just needed that little help to tell you exactly what to do. So we have been working in my team for a few years now on trying to develop these systems that provide some of this help. Let me switch to optimization of video. And essentially, we we have done this work that is called You Do I Learn, where essentially we have a group of people that is trying to observe the world, and as they observe the world, they are the video is not playing. I'm sorry. Let me see if I can try again. Okay, hopefully next videos are going to play. But essentially, we have a lot of people trying to observe the world, and as they observe the world, the system automatically starts realizing what parts of the object are interacted with and how they are interacted with. So the system automatically extracts these key locations and ways in which objects are used, and with that, it creates a dictionary of videos, of small video guides, so that when next time someone watches this panel in the printer, they actually get a small video that tells them how someone else has used that panel before. This is actually quite interesting from the point of view of scaling content creation, because it's no longer creating these fancy 3D models. It's actually tapping into this motor mirror neuron system that humans and animals have, that if you see someone doing something, you can actually imitate what they are doing. And so we also develop other systems that that are also along the lines of okay. So actually that was playing. So that was the You Do I Learn, but I'm now going to switch to this Glacier demo. Let me optimize for video, and by all means, please let me know if the video is not coming through well. But essentially, in this case, there is a person that is moving in the world, is observing things, doing things. We have implemented this in Google Glass. So in this case, it's a much more simpler system. It's just connecting an object detector with the IMU information on Google Glass to detect that the person is doing something, paying attention on something, and the system automatically captures video. That is. So the person just goes, interacts with the world, interacts with different machines, and later someone else is going to interact with this. So in this case, it's this person is looking at these different objects and is given these videos that are part of the collection that the system captured in order to help that person to know how that video is working. I don't know what's going on with my video player. Apologies for that. Okay, so this is one system that essentially combines how to model user attention, how to extract relevant information from observations, and how to redetect previously interacted objects. And just these very basic components, all working in something as simple and basic as Google Glass from several years ago, already allows people to make progress in terms of understanding how to use some of the things that are out there. Now, some of the things we had to do here is Google Glass, for example, does not really have a good way in which you can use where the person is looking at from the point of view of gaze. So it has no gaze tracker. So we actually learn from IMU signals where people is looking at. And there is a very good correlation when you're trying to manipulate something of where your head is. So where you're paying attention, the angular velocity of your head is relatively small when you're paying attention or fixating on something. So essentially we can learn where the person is looking at based on just the IMU signals. So we published that paper in IS International Symposium of Wearable Computing in 2015. And so when you put everything together, essentially you have a system like this, where the system looks at people, not just one person, but multiple people. In this case, how to set up an oscilloscope. So there are like several steps in there and many different buttons that you could interact with, but essentially at every step, you might only be interacting with a few buttons. And then the system captures this small video guide, automatically deciding when to start, when to stop, and all based on the angular velocity of the head. And so we capture these videos from multiple people. And so we have this dictionary of small videos that later we can replay to people, and we do this for different objects and so on. So eventually, when a new person comes and looks at this object, it gets these video guides that tell that person how to do something. So again, remember that this is an attempt to try to deal with one of the bottlenecks in egocentric vision, how to deal with the amount of information. In this case, is done by fixating on only small moments when the person is paying attention or fixating into something, and only capturing information that is very close in time to that moment. Overall, if you compare this type of guidance with this automatically extracted guidance with guidance that has been manually curated, then you can find that essentially they perform exactly the same. So this is quite encouraging, I say, from the point of view of trying to build a catalog of experiences around the world. We have been recording the world from the point of view of pictures or videos, but the connection of experiences around how to operate or how to do things in the world, that's still to be done. And I think this type of methods could be a way into that. Now, the next problem that I also talked about, how can your system actually decide that you are requiring help? And one of the things that we started doing in here is how to decide from your collection of videos that you might have about doing a task, how to decide who is better and who is best. So how to develop some ranking. So we have this CVPR 2018 paper, which is called "Who is Better, Who is Best?" And essentially, we have collections of videos, egocentric and not egocentric, that essentially aim to say, from these two videos of this person or these two different people doing exactly the same task, which one is better and which one is not so good. So we can essentially try to learn using, in this case, a deep learning method, how to rank these videos in terms of proficiency. And again, this will be one way in which we can try to start to organize the value of the value of these video collections that we can in principle capture. So let me play this video. Let me optimize again for video. Let me play this video, which is from our latest CVPR 2019 version. And let me increase the volume. Hopefully, let me know if the volume is not coming through well.
When assessing skill in long video, there may be variability in the skill exhibited throughout a video. In this example, the left video shows better skill in egg cracking. However, as the videos proceed, higher overall skill is shown in the right-hand video. Trained attention can also exclude parts irrelevant for skill assessment. Next, present qualitative results. We show video segments with strong attention responses for the low skill module from various tasks. In surgery, Strain on the material is a sign of low skill present in only low-ranked videos. In Apply Eyeliner, segments show mistakes being fixed. In Origami, the module attends to undoing previous folds. For high-skill module attention responses, consistent performance can be seen in the segments, with straightening edges in dough rolling and origami. Interestingly for drawing, pausing to consider is indicative of high skill. Next, we show videos ranked by our method and demonstrate the varying attention over time. Response of the high skill module, in green, show increased attention when a bean is being picked up. The low skill module, shown in red, attends to difficulties in gripping beans. In Tai Tai, we see that, for the most part, our method correctly ranks pairs of videos. It only struggles with pairs close in the ranking, such as the first and second videos displayed here. These are swapped in the ground truth. For longer tasks, such as scrambling eggs, filter responses are more sparse. Green demonstrates segments attended to by the high skill module, while red indicates the low skill module's attention weighting.
Okay, so this is the PhD work of Hazel Doughty in collaboration with my colleague Lima at Bristol, where I do think that this is quite a fundamental part of egocentric perception, how to understand skill. And this is a line of work that we have developed. We have recently also launched, if you're interested in this line of work, we have launched and released a data set which is called Epic Tent. And this is about people assembling a camping tent. We have 29 participants and over 7 hours of video, people doing this task, which we consider as a challenge because, of course, it's a non-rigid object. So this thing is actually changing shape as you're building it. And so this data set, I think, is actually quite rich from the point of view, very challenging, but quite rich from the point of view of the type of hand object interactions that you can have there. So it's a good thing that you might want to consider for next generation and complexity in egocentric perception. So the final thing that I want to highlight that we've been doing is this work with Eduardo Ruiz, who recently completed his PhD. And what we looked at here is affordance determination. You may have come across this term in egocentric perception for sure, but this is actually quite a very important line of work that I think is still to be done, and it's something that connects research in egocentric platform, not just people in the loop, but also robotics. And it starts with some basic questions and observations about the world. So if I show you this picture here, and if I ask you what is this, I think there will be a very obvious answer that we can expect. Apologies if the video is not coming through. Sorry, the picture is not coming through. But the most obvious answer when I ask people in a room, what is this? Is, well, this is a glass. And what is a glass good for? Well, this is good for putting water or a liquid in there and maybe drinking. But the reality is that this object can be used for a number of things. It can be a paperweight, if you wish, and you can even use it for building castles in the beach. So what I'm trying to highlight here, something that obviously many others have highlighted before, but I think it's still important to highlight. This obsession of classifying the world with labels is something that we're embracing quite well in the deep learning era of computer vision, precisely because our tools require this data, and most of this data is labeled, and if it is not labeled, then we don't even use it. But I think there is a danger of trying to describe the world in ways which are unnatural, like forcing that this object and what you can do with this object is only limited by what you have labels for, or what favorite labels you have it annotated under. So this is why the look at the world from a different perspective, which I believe is along the lines of affordances that were introduced conceptually many years ago, is very important. So the concept of affordance is how can we actually understand the world based on what we can do with that object or that scene. What can we do with that, rather than trying to label this object as a chair? So a chair may not necessarily be just for sitting. It's just an object that allows you to do certain things, which includes sitting perhaps, but you can use that chair for other things which are not for sitting. And you can also sit in other places that you will not normally consider it to be a chair. So again, hopefully this type of concepts like affordances, when in my opinion dealt with correctly, can rescue us from surrendering to data statistics. So there is no denial that affordances are elusive to define. A lot of people have struggled with trying to understand this concept. But one thing that is out there is that a lot of people agree that for an affordance to exist, there is some sort of interaction between the scene and the object. It's not about classifying things into arbitrary categories, as I argued before. It's what can you do between the actions that you want to take and what is out there in the world. So affordance research in computer vision and robotics has indeed been done quite a lot, but in my opinion, it's quite unfortunate that many of these attempts start with precisely what affordances are not meant to be. So they're not meant to classify the world. So if we do affordance research with classification in mind, I think we're doing step backwards. But what are we talking about when we say that we want to detect affordances? So in this case, there's a robot observes a scene. What can it do in that scene? So how can it start realizing that it can place these objects in these locations? It can hang these objects in these other locations. How can an object? How can a system, either a person or a robot in the loop of the system, realize that? So one of the things that we have done in my lab with Eduardo and now a new PhD student, Abel, we've been looking at developing a concept that we call the interaction tensor. The interaction tensor is actually based on a very, very basic and fundamental geometric principle, which is called the bisector surface. What is that? So imagine that you have two objects, one in blue, one in green, and the relationship, the geometric relationship that exists between these two objects is this bisector surface. So this surface is essentially composed by points that exist that exist between the two elements that we're trying to describe. So we can essentially define something that geometrically talks about the relationship between these two objects. And what we did next, what we call the interaction tensor, is we essentially said, well, this bisector surface is nice, but it doesn't really tell us about more about the specific relationship between these two objects. So what we introduced is something very basic, which is just the vectors from where the points in the bisector surface come from, and we use them as the descriptors of the interaction that exists between the two objects. Hopefully this is making sense. But if not, we have a paper in ICPR 2018 and now a recent one in Frontiers Robotics last year that describes more in detail. But what I want to show you is what happens when you compute this interaction tensor, this collection of vectors that describe the bisector surface. So what you see is that if you have two objects, let's say the sink and this cup in here, the interaction tensor looks like this. So this is all the vectors. You don't have to use all the vectors. We actually just use a very small a fraction of them. Again, more details in the paper. But what I want to point out is that this scene object, which is the sink, with different objects. So you can see this is a pot, this is a jug, this is a bucket. All of them, when we're trying to describe this relationship that exists between this sink and this other object that seems to be like a container of something, produce very similar interaction tensors, even if the objects are very different. So this is actually quite interesting. And the other way also happens that when the scene changes, so you have a chair here, you have a coat hanger, or like in a wall or standing, and even a sink in here. When you describe the local geometrical interaction between these two objects, all of them have very close similarities. So what this is saying is that there are ways in which we can describe these very complex relationships among very different objects with essentially very little data. Because, and this is what we have done, with a single example, let's say you take this example here of the coat hanger, or this example here with the cup, we want to describe all these other interactions. So we want a robot or a human to find all these other ways in which, all these other places where you can actually describe and find these interactions in there. So we have tested this in a number of ways. Let me clarify, the interaction tensor does use RGB data. We have tested with both synthetic images like this and RGB data. Interesting things will happen, like from a single example, you're able to find things like you can place a coat hanger, as I have done many times, in a shelf like that, even if you just trained it with a standard railing. And if I challenge deep learning methods that requires hundreds or thousands, perhaps even millions of examples, the chances of me developing a system that from a single example that I show you how I can hang this coat hanger, and then suddenly I can find a totally different way in which I can place it, it will be a very big challenge. What you can see here is someone riding a motorcycle. And I remember at the time when my son was three years old, he will play pretend that there was a motorcycle in the arms of the sofa, and this type of method can find that. Something like this is the naive ICP approach, but we have also tested this with deep learning approaches. This geometric representation is far better. And more recently, we have also combined deep learning for saliency, not for the description of the actual interaction, but just for having a hunch of where in the scene there's a chance that something could happen. And then we go and use the interaction tensor. So we combine deep learning saliency with the interaction tensor in order to find hundreds of affordances in real time. So there is also code available out there for you to test this, and so you can find these different examples here. Let me just see if I can play this video.
Scalable real time
and so essentially what you can see here is the camera is exploring this environment and finding places where you could do these different things. A lot of the things that we do in the world have to do with just placing, so that's probably not so interesting. But you can start finding things like you can sit in here, you can feel something in there, and some of these scenes include RGB data, as you can see. Certainly, you can find the obvious one, which is riding that motorcycle and so on, but other things that may be less expectable, like can you hang this jug in here in the tap? Yes, you can, and all of these were produced from a single example in geometry. So I will be closing now. Essentially, what is still to be done? Let me go back to those 3 points that I talked about before. So dealing with scale and achieving scalability in egocentric vision, I believe, is still a big challenge. Learning from and helping millions of users is likely going to be a big question still remaining. Understanding the context beyond location, for example, via affordances or other world primitives that ideally do not require these masses of learning that we have become accustomed to, I do believe is going to also be quite important and interesting. It's not to say that methods that require learning are bad. Of course, learning can be and is very useful. But if we can reduce our reliance on assuming that we're required to see this specific way in which objects are interacting with the world or instances of cases in the world, I think we are missing a lot if we still think that that is required. And then the other big one, which of course is across the entire human-computer interaction field, is how can we understand users better? How can we model? And for example, in the case of skill learning, how can I know that you actually need help? And how can I know that that you still have something more to grow in terms of learning something? So with this, I finish, and hopefully you got something out of there, either from a look at the back of early research or some directions. But I will be happy if there is time to answer your questions. If there is no time, then by all means, I'm super happy to hear from you via email or LinkedIn, for example. Thank you.
Many thanks, Valterio. The talk was amazing. I was really amazed to hear about, like, it was for me the first time to hear about, like, we can look at the data in another way too. We have time for taking some questions. If there is any question, please raise hands.
Can I make a question to Valterio?
Of course, Vittorio, please.
Hi. Okay, thanks, Valterio, for the nice talk. I also think that some of the stuff which was in a way dealt with 20 years ago, or now is a more revisiting with deep learning. I have a question, quick question for the last your last work about affordances. Mm-hmm. Essentially, so I also worked a bit in the past about this kind of stuff. And but by the way you introduce these affordances, it's not actually more related to, in a way, labeling the object, but rather the use you can do with the object. Mm-hmm. Did you have explored or investigated the ideas of the use of an object, what a human being can do with an object in the context of the scene, in the sense that now you, with an interaction tensor, you in a way try to codify which are the most likely use of the object in the context of the scene. So it's a sort of, as you said, object scene interaction. So what about if you put the human in the loop and you have an object which can be used by a human to make something in the scene?
That's a great question. Thank you very much for asking, because it also helps me to clarify that affordance research, I think, is only in its infancy. And especially because, as I mentioned before, there's quite a lot of work that does require this labeling, that is labeled as affordance research, which I don't think it's really going to take us much forward. But your question is interesting, and that is why we have we have classified our work as geometric affordances. We're not really touching into dynamic affordances yet, or as you say, how can I discover from what I have available? This is like an old problem in robotics. The robot is in a room and there are 4 boxes and a crossbar. What can the robot do with that? Yeah, and the same for a human. I think there is quite a lot of work that still needs to be done. With the interaction tensor work, what we're trying to do is indeed challenge some of the assumptions that you need data in order to understand the world, and trying to see how we can better define the interaction between the scene and the object. But to your point, I think there is still some work. I mean, we have some ideas, but we're still working on that. In terms of how can we take that concept forward and bring it to dynamic affordances, or affordances where maybe there is no obvious example of what you want to do. So you're quite right that there is quite a lot of work to be done in there, and our work is only scratching the surface in terms of what needs to happen in affordances, and that's why it's one of the things that I'm calling out as still to be done. Hopefully that makes sense. So I don't have a good algorithm yet, but I do encourage anyone to look into solutions for that, especially if you can avoid the temptation of using a lot of data. I mean, you can use a lot of data to validate, but not necessarily requiring a lot of data to function.
Okay, thanks. Thank you.
Thank you.
Well, thank you. If, I do not see any raised hand, so if not, we can thank again our speaker, and yeah, move to the paper, first paper of this session. Thank you, Walterio.
Thank you, Walterio.
Thank you all. Thank you.
Thank you.
My pleasure.
Thank you.
So, is Alejandro here?
Hi, I'm here.
So you will be presenting the paper yourself, or playing the video?
I would like to play the video.
Okay, sure. So go ahead, please.
Okay, I'm not sure if you can see me.
We can see you, yes, but you need to be also sharing your screen.
Yeah.
Yes, perfect.
Right?
Yeah.
Perfect.
Just raise up the volume of the computer PC you're using.
Okay. So.
Hi, my name is Alejandro Cartas, and today I will present our work Understanding Event Genres for Egocentric Activity Recognition from Photo Streams. So this is today's presentation's outline. I will first describe what are egocentric photo streams and egocentric action recognition on them. Then I will present the motivation of this work, and it will be followed by the method, the experimental setting, the results, and the conclusions. So first, I will present this broad introduction to photo streams. So photo streams can be acquired by live logging camera or photo streams camera. These are usually necklace camera, like this one displayed at the bottom. This person is a narrative camera. So with this kind of cameras, they can be worn throughout a whole day, and it can generate around 2,000 images. So here, at your right, you can see images captured by them. With this specific camera, you will get some issues like the bad image quality, and also, more important, the low frame rate. So in this example, each image is separated by each other by 30 seconds. So you might not get niceties such as optical flow. And finally, they have several occlusions provided by the different body positions. So now, what in the last years, I'm working on egocentric action recognition. It tries to determine what a person is doing from or his perspective. So the characteristic problem is that the person itself is only partially visible in the images through his hands. So this task, it depends on the context. So you can make the prediction by what objects the person is manipulated, other people, and the scene itself. So in this example, you can see a clear difference between the third person and the first person perspective. You can see in your right a person riding a bike by looking at the handlebar and also the hand. So now we define what are action and activity in these settings. So our taxonomy is in terms of the length of time. So an action can be as short as 1 millisecond or as long as a few minutes. And an activity is composed of 2 or more actions, and its duration starts at the seconds scale. So here in this slide, you can see the difference between video cameras and photo stream cameras. So at the bottom, you could see a person in a kitchen. In the first frame, it's looking out the fridge, and then it's, I don't know, it's around the kitchen. So you'd say that the activity, she or he is cooking. So with the video cameras, with only 30 seconds, you can capture a lot of information, and this information uh, it is well determined into actions, and then in an activity, this person was preparing an American breakfast. Now, the motivation of this work, well, we started with the temporal coherence. The temporal coherence is the tendency of similar concepts to appear in neighboring frames of a sequence. So it is really helpful in the presence of occlusions and changes field of view. So in this example, you might be wondering, what is this person doing in the night in the street? So this person might be walking or might be seated, or it might be standing by. So in order to disambiguate the activity this person is doing, you have to look close at nearby frames. So now that you look at them, we can tell that this person was riding a bike, but you didn't see the handlebar in that specific picture. The other concept that we felt it was important, and it was we had to do a study. It's the event boundaries. Events are groups of sequential images that are homogeneous with respect to a given criterion. So in this example, you have a sequence that starts at the upper left here and finishes at the lower right. So if you determine some the events of what's going on, like you could have a criterion of the places the person is being, like this one, you might get these events, and with these events you might train a model, and hopefully it will determine what action the person, he or she, is doing. So now I will present our method. It's really based on this idea of the events. So first you cluster the sequence into subsequences. In our work, we did it with the contextual event segmentation and with the SR clustering. So then with these events, we train a model using the boundaries. So in this example, you can see that the person having a meal, then riding a bike, and then walking to the beach. So if you first clustering, you might get these events, and then with these events you get these boundaries, and with these boundaries you can train an architecture like a CNN that captures space relationships, with LSTM to capture temporal dependencies. So now in the experimental settings, well, we use a similar data split on the activities for daily living egocentric data set that we presented before, like a few months before this paper was submitted. We consider training the CNN plus omnidirectional and a bidirectional LSTM using the full sequence. The event clustering was, as I already said, performed by the SR clustering and the SES algorithm. But in this slide, I will only present the SES result. To really briefly, we use the exception network in comparison with the first paper we presented. And we also use the mean average prediction because this task can be seen also as an action detection task. So now the activities of daily living egocentric data set consists on around 100,000 labeled pictures, labeled in 35 different categories. In doing the labeling, we consider the temporal coherence. We just see individual frames. These images were captured by 15 graduate students that wore the camera around 15 days. So we more or less we cover 191 different days of images. Now, to make a robust evaluation, we presented very specific split. So it's important for me to describe it because it also appears on the results. So first, previous works consider only a random split. So in this example, you have a person and 2 days of activities in which each rectangle represents an image. So in the random split, you simply take the frames and you put ones in the training set and the other ones in the test set. The problem with this kind of random split is that you might end up splitting consecutive frames, and these consecutive frames could look similar. So in this example, shopping doesn't look really similar, although they were consecutive. But using the computer, it really looks almost the same. So we propose to use a temporal split. In the temporal split, you group whole days and you send one to the training set and another one to the test set, making an unseen full sequences. So if you want representative data splits, you might be getting a computationally expensive problem, and you might end up having unbalanced splits. In this case, the yellow images might just end up in the training set, but in the plus side, you can test sequences. And finally, a better temporal split is given if you also consider unseen users in the test set. So now you have, here's the full description of the experimental settings. Now let's go to the results. So in the results, here are just for the exception network once again. So this table could be confusing. So let me show you first the first division. So at the top, you see the seen users that I described, and also the unseen users that I described. The next division is the results given for the unidirectional LSTM and the bidirectional LSTM. Now, each column on this table, the first one represents the no boundaries, using no boundaries with the full sequences, then using the events, and then the ground truth boundaries. So we train the method using the ground truth boundaries given by the label data, and we test it on the label data. So now, the first thing that we could see in this table is that the boundaries didn't help the bidirectional architecture So you could see that even using no boundary was even better than the ground truth boundaries. Now, the next thing you can see in this table is that the best results were obtained for using events on the seen users split, but for the unseen users, the using no boundaries was better. But still, you could see that the ground truth boundaries persist. So they are really important for training the method. So now, if both splits, if the seen and the unseen splits, you join them, these are the results. So you got a better accuracy for the events, but overall, using no boundaries were the most robust. So finally, I will present the conclusion on this work. So what we tried to do in this paper was we empirically studied the effect of event boundaries for activity recognition in egocentric photo streams. We empirically found that event boundaries improve the performance of the CNN plus LSTM architecture on previously seen users, obtaining for 85.73% in accuracy. And we also consider that our intuition and our method didn't really perform so well because of the context ambiguity. Because a person can be doing many things at the same time in the same place. So a person could be not only working in his desk, but also drinking something or eating something. So this task involves have to consider this context ambiguity of multi-level problem. So thank you very much, and I hope you could take a look at our paper. It has more details and more experiments that were not really covering this quick summary. Thank you very much.
Well, thank you. So we can be taking questions. Are there any questions?
I can be asking if there is no one else.
Yes, please, Chidan, go ahead.
Thank you, Alejandro, for the presentation. One thing is quite not clear for me, which is that how do you define the event boundaries, especially given that people might be doing a lot of activities at the same time? It's not clear for me. Can you give some intuition?
Well, on this paper, we perform a temporal cluster. We use two methods. So basically, these two methods only describes like the scene, only captures similar scene context. So what you will get from these clusters are just the person in a specific location. So in the future lines, what we are saying is that these results they don't really perform extremely better. So that might be because of a person doing many things in the same place, and we couldn't capture that. So that's why we consider that there is an ambiguity.
Okay, so the boundaries are by an automatic clustering algorithm.
Exactly.
Is there a sanity check by humans, or do you somehow?
No, we use well the annotating process consisted in the same people labeling their sequences. So these boundaries that the people obtained, like telling what were they doing, were the ground truth.
Okay. Okay. Now clear. Okay. Thank you.
I also had one question. I think I saw that the results that you got with CNN plus LSTM were better than the results achieved by CNN plus by LSTM, bi-directional LSTM. Is that right?
Yes, that's right.
Is there a specific reason for that? Have you thought further about it? Why is that happening?
Well, we don't have really clear what's going on there. Mainly because well, we when we started this project, we hoped that this bidirectionality works in our favor, but it didn't. And also, when we tried on full sequences, we didn't really pass much of. We could have trained the LSTM passing a lot of sequences from different starting points, and it seems that if we did this kind of training, the temporal boundaries were not their importance wouldn't be you couldn't see the results on the results. You couldn't see the effects on the results if you didn't this kind of training. So we think that the LSTM with other kind of trainings, we consider that it's being used as a filter. So that's why we kept on full sequences. And well, the conclusion is that with this kind of LSTM, you cannot catch the really well like the temporality, which you are catching, like you are kind of smoothing the sequence. So I think there is much work on that sense.
Well, thank you for your response, and thank you for your presentation. I think we can be moving to the next and last paper to be presented today. Alejandro, I would like to ask you to stop sharing your screen.
Okay.
It's got to be on the top of the screen. So the next paper is EgoMap, hierarchical first-person semantic mapping. Thomas Stuver, I'm not sure how to pronounce the name well. I'm sorry.
Never mind. No, never mind. Can you hear me?
Yes, I can hear you.
Okay, well, good. Then everybody, I suppose, can hear me. Let me share the screen.
So how is the correct pronunciation of your name?
Well, it's Shuvegesh. But I can't share the screen. It says that.
I think it is because Alejandro is still sharing.
Yeah, because another applicant is sharing, it says to me.
Yeah, but I think Alejandro is sort of, freezed. Let me see if I can.
Yeah, well, the last screenshot from his screen, it says power off. So I guess he powered off his computer. Okay.
Oh, okay. Now you should be able to share the screen.
Okay, so. Can you see my screen?
Yes, perfectly.
Good. Okay. So let's start then. So my name is Tamás Süveges, and I'll be presenting EgoMap hierarchical first-person semantic mapping. So we consider an unsupervised learning of semantic user-specific maps from first-person video. Okay, so that the task we address can be thought of as a semantic, non-geometric form of simultaneous localization and mapping that is actually different from typical formulations in robotics. The resulting map is what we want to get as a resulting map. We wanted to capture location that represents human intuition. So for example, a motivation application, consider a voice output communication aid for non-speaking users. Those users often average between 8 to 12 spoken words per minute, but a typical adult can easily get to 150, 190 words per minute, which is a big difference. So one approach to offer them better predictive text is and improve their communication speed is to leverage information about the context. A user-specific map would enable that the user's communication can be contextualized in terms of location they visited, which then can be used to improve language prediction. Other applications could involve aid for memory loss, as well as automatic visual personal history generation, potentially combined with activity recognition. So in this presentation, first, I will discuss our unique world representation, followed by an explanation on how to localize the user in this representation. I will also cover map learning and our custom dataset supporting the challenge we outline in our paper. And finally, I will present some results. Okay, so our aim is to define a map representation that reflects human intuition, which can be learned online from an egocentric video source. So we imagine a user to travel through their everyday environment and perform tasks visiting different locations. The locations in our model are conceived as places where the user stays for some time, so often to perform a specific task in there. And we find that they tend to correspond to places which people might refer in narrative. So for example, my desk, my school kitchen, or the meeting room. We will call these locations stations, and we do in our paper and this presentation. So those are stations. So we introduce a hierarchical map structure in which stations in a map are represented in terms of view graphs. So our map can be written as a weighted directed graph as seen on the left here in this slide, and each station in turn represented as a directed graph as shown on the right. Each station, on the left, we illustrate a map with five stations and multiple transitions. The visual appearance of the arrows represents the number of transitions between two stations. Similarly, on the right, we illustrate a single station with 4 views in it. To identify video segments related to stations, we perform motion analysis to detect sections without significant transitional components, to which we refer as a visit. So that's a visit without a significant transitional component. The video now shows a visit. Let me start it. Okay. So the video now shows a visit. And once we experience significant transitional motion in the left top corner, we see it's not a visit anymore. But once such motion ceases, you will see in a second, then it will again be considered that the user is experiencing a new visit. And so visit is not true. So the user is in a new visit now. So once segmented, visits are intercepted with periods of transitions characterized, for example, by sustained motion, sustained walking, as we've seen in this example video. At each frame of a visit, we consider a detector model that produces d-dimensional binary observations. The false positive and false negative probability are parameters of the detector, and they denote the quality of a feature. We used fixed parameters for all features in our experiment. We also consider views to be modeled by a d-dimensional vector where elements are probabilities of a feature being detected at the view. So when used for view prediction, we consider independence between features for simplification to obtain the observation likelihood. In common with many work, for these features, we use a binary version of bag of visual words descriptor. Given our hierarchical representation, we use recursive Bayes to estimate both the current view and the current station given an observation sequence for the current visit and all preceding visits. In this slide, VT is a random variable over all views at the station, and LT is a random variable over all stations learned so far. At the start of the first visit, we assume that the user can be at any stations with equal probability. And at the start of a visit, although we could actually obtain a prior distribution over the views at the station using weighted connections from between views from different stations, for simplicity, we just instead assume independence between views from different stations and use a flat prior to assign equal probability to each view. To decide on new views, we adjust the denominator of our recursive Bayes equation so that the probabilities of the known views at the station sums to less than 1, leaving some probability mass assigned elsewhere. So an elsewhere means for a new station or view. And similarly, we use the same approach to detect new stations. However, in both cases, in our paper, we highlight that it can be calculated by a summation, but the summation cannot be evaluated properly because that would require knowledge on every yet to be seen views and stations, which is obviously impossible. So instead, for views, we do a mean field approximation. And for stations, we define a likelihood threshold. And we give more details about the update process in our paper in section 6A and section 6C. So I will omit that for this. So in this slide, we summarize our localization and mapping process, which can be thought of as a two-pass process. During a visit, localization is facilitated to provide online information where the user is. Once a visit terminates, we make a decision and either associate a visit with a known station or create a new station. In the second pass, we use observations collected during a visit to update or create views. For each observation, we once again decide whether it belongs to a previously seen view or a new view. The outcome determines whether a new view is created or an existing one is updated. So during this project, we recorded 4 hours of video over 5 mornings of a user's activity on the university campus. That was before coronavirus. This activity was loosely scripted in order to make sure that enough visits were made to each stations. This script consisted of list of stations along with suggestions for activities during station visits. And in this slide, we provide image examples from 4 stations in our data set, as well as a script extract for the first video. Okay, so here we show a video example of a process of a view generation during a visit. At the start, we have a single view, but as the user turns around, we can see more views are appearing and potentially correctly relocalizing. So right now it's in view 4, and then, oops, sorry. And then when he goes back, then it's view 3 again. So the green color denotes the current, the estimated current view with the maximum posterior probability. This video is probably more interesting. So in this video, you will see a live map building in terms of a graph. The node in the graph will represent locations, and the color of them refer to the result of the location. So similarly to the previous video, when a node is red, then the visit is believed to, when all node is red, the visit is believed to belong to a new station, and the green color denotes the station with maximum posterior probability. So as you can see in the video, the user started at the entrance, that was location 0, and now he is in a 3D lab. This location is called 3D lab in our data set, and the 0th node is red because the system thinks it's a new station correctly. And as we progress, the user visits a new station again. That's a kitchen. But when we revisit the location, the map correctly re-identifies the station as the first node, because that was the node which was created when he first visited this location. So I will let this video go through so you can have an idea what is happening. So again, it's re-localized in kitchen. So that was node 2. And again, so I think everyone have the idea. So to evaluate this mapping, we use mutual information score that is frequently employed to assess clustering with performance. However, mutual information score tend to be higher when the node count is higher. Therefore, we instead use an adjusted version of it, and the adjusted mutual information score. The new station likelihood is basically the threshold. The new station likelihood threshold is an important free parameter in our system, which is basically directly controls the final station count. So we report performance for different values, allowing us to compare predicted maps with varying number of stations. We provide the baseline result, for which we use the simple offline k-mean to discover stations from the video. We also present results for a partial version of our system in which we represent each station with a single view. So every station will just basically be represented by one descriptor. And we conclude that EgoMap outperforms our baseline approach, and that the view graph does have a positive effect as well. So in our paper, we reported preliminary result for experiment on some videos from the ADL dataset, number 3 for 3 videos, and the results were acquired from these 3 videos with 6 and 3 stations. These results suggested that the hierarchical representation we use tends to help. However, the results were a bit noisy given the low visit and station count. In the next slide here, we show one way to visualize an example map and its correspondence with ground truths. The ground truth map is shown on the left, and its 9 stations are represented around the perimeter. The internal connection represents transitions that occur between those stations. On the right, we show a learned map and the ground truth map together. Stations in the learned map appear around the bottom half of the circle. Connection represent matching of visits to stations on the learned map with ground truth stations. The size of the representation of each station in the learned map correlates with the number of visits to the station. So in this example, some ground truth station connected with multiple nodes in the learned map. For example, 3D Lab is matched with 3 nodes. This suggests that the threshold that controls the new station was too high, causing the model to generate too many stations. On the other hand, one learn node is well connected with both lab and 3D Lab. And this suggests that, well, actually those stations have strong visual aliasing because of a computer monitor being at the center of the view. So that might explain why it was merged. So to summarize, we formulated a new person-centric simultaneous localization and mapping task and described a modular hierarchical probabilistic framework to tackle that. Unsupervised sequential learning of semantic user-specific map from first-person video enabled us to build a user-specific representation. These maps represent a network of visited stations and model each station as a network of views. We combined the data set and contributed the data set and evaluated performance in terms of map correctness. Future work could include testing our method on other data sets, as well as adding more measures that relate to localization and performance in some real world application. Yeah, so that's it.
Well, thank you for your presentation. Are there any questions? So I understand that there's no question from the audience. I would like to ask you a question. Why did you decide to create your own data set, if I may ask? Yeah, go ahead.
That is a good question. And I think you were about to say that there are existing data sets.
I assume there should be, but I was not sure.
But there isn't too much, actually. The thing is that we kind of explore a new area with the fusion of egocentric vision and simultaneous localization and mapping. And for those data sets that are recorded for simultaneous localization mapping are captured from a robot, and it just travels through the environment, scans the environment, because in robotics it's usually the key thing is to localize accurately the robot in the 3D environment, and it doesn't stop and start watching some thing and watch the TV. So there isn't any important location we could find in those data sets given our motion analysis. On the other hand, in the egocentric world, many data set is tailored for activity recognition. And what they do is they record small video sections of activities and that's it. So they don't record a whole day or a whole sequence. They just give chunks of videos. And it's hard to, it's impossible to recover any transition from them, let alone we need more example video section of the same location so we can relocalize the user in it. There are very few data sets. As I mentioned, we reported for the ADL data set, but it's still, they have a very limited station count compared to our data sets. It was 4, 6 and 3 stations for the videos we considered. and we have 9, and that's not just the station count, it's the visit count, how much the user revisits those stations, and that was 6 and 14 for those videos, and we have just over 100 visits. So there are some which fits, but it's not as extensive as ours, and it wasn't, you know, we couldn't get accurate results for those, let alone interesting ones.
Sure. So possibly you can be expecting quite some people referring to you because of your data set.
Hopefully. Hopefully.
Yeah. Well, thank you for your presentation. I assume there is no more questions because there is no raised hands. So I think here we can already close the session, close the workshop. We have started the workshop basically with a sequence of thank yous. I would like to close the workshop also with a sequence of thank yous. Thank you to the speakers, of course, for being here. Thanks to the authors for becoming present and presenting their work and answering to the questions. And thanks to the audience that they were here almost until the last moment.